let's talk about what the problem is. I'll do a little bit more intro-y than I normally do. So, the problem, it's useful in many ways, but the specific example of this came up in 3D, and I'm only going to do it in 2D, in Dwarf Fortress. The idea is that you're pathfinding in a game. So you have a big 2D grid, and you're pathfinding on it. And what happens is, if you can't actually reach the target, if your starting point and your end point, they're not reachable to each other, your pathfind is going to search the whole entire map, everything that's reachable from the start point, depending on the algorithm you're using, before giving up. And that's really inefficient. So it would be nice if you could have some kind of data structure that you could query efficiently and say whether 2 points are reachable to each other. And there's a pretty well-known algorithm for taking a graph and finding all of the connected components in it. And if you do this, you label each node in the graph with which component it belongs to. You can check whether two things are reachable by checking if they're in the same component. So you just look at the label for each one and you say they're the same, they're reachable. So what is the problem? Okay, so there's a good, well-known algorithm for how to create, given a graph, how to find these connected components, the disjoint set forest, which is basically order n time on n nodes. So for a big grid, we tend to think of n as one side, so there are n squared nodes, so it's order n squared time, which is, when you're starting from scratch, that's as fast as possible. Now, the actual disjoint set forest algorithm is the place where people learn in college about inverse Ackermann function, or the Ackermann function, which is a function that grows so incredibly fast. The actual performance of the algorithm was order n inverse Ackermann function of n. And the inverse Ackermann function of n is bounded basically by 6 for, say, the number of atoms in the universe or something like that. That function will come out to 6. So it's pretty much a constant factor. Now, the full-blown version of the disjoint set forest algorithm is something I don't actually know offhand how to do. I always only do one part of the speed up to it. And because we want a reference solution, and a reference timing, because we're going to do an incremental one as well, I want to start by coding up the disjoint set forest version, and we'll use that to get some initial timings and to check the basic connected components. So I need a map. I don't know. Probably the best thing to do is just take a photograph and threshold it, maybe. Anybody had a recommendation for a good photograph? That's a little too small. Are there any big ones? Here we go. What's the easiest way to copy this into the... Can you copy an image? Yes, you can copy an image. Woohoo. Okay. So what happens when we threshold this? Let's actually get more of it. Then let's actually do curves. Which one's curves? I don't remember. Image adjustments, curves. I control that, of course. And this will let us get some more complexity in here. Okay, and then threshold it. Okay, so that's going to have like lots of little bits of noise. So let's run. What do I want? Filter, other min, max. I want min to remove the, oh, that's too big. 1. Okay. And then max. All right, it's still pretty, still got lots of these little things. But hey, that's probably a good test case. All right. And then I'll just, so I'm going to do something smarter later, but I just wanted an initial test thing. So let's do this. Actually, I want pen mode, pencil mode. Blah. Come on. There you go. And we want white. So just to make sure all that stuff is connected. Because, yeah, I think it was disconnected through that. All right, there we go. And I'll save that out. Map 01.png. Why is that? Oh, because it's got layers. All right. Now, while I was doing that, I actually covered up the chat, so let me see what the chat is up to. Yeah, continuous region coloring is a reasonable way of referring to this. All right, map 01. What's the order these are in? Type. It didn't autocomplete for me, unfortunately. Did I get the name wrong? XYN. All right, we want to force this to be single channel. All right, so now, what do we do? We're just gonna see the pants this here in a hacky way to start with. Whoops. 8, no, 16. No, it's 1K by 1K, so okay, we'll just do it this way. All right. I don't remember how you name these, so let's just do it like this. So find, we want to find the leader for a given point. And the way we do that, so you say p equals leader of y of x, if p dot x equals x, and p dot y equals y. If it's its own leader, then we return it. Otherwise, we return the leader of that. So, so the disjoint set force algorithm, the way this works is, so the whole thing to understand about this problem, what we're trying to solve is that when you have this big, oh, I don't have it open anymore. When you have this big map, I imagine it's been colored in, so like all of these are all different colors, and then all of this is one big color. When you have that, and then you add a new connection somewhere, you need to go change, if you connected two things, like if you had two big regions that were disconnected, you now need to recolor a whole big region. And vice versa, if all of these are one big region and I break the connection here, one or the other side, all of those have to be recolored. So on the face of it, you might think it's not possible to do efficiently. But there's a trick. If for every single node, instead of storing a label, we store a pointer to a label, then we can say, like, all of these, imagine it's split. All of these ones here point to address A, and all these ones up here point to address B, and in address A and address B are the label. Then when we merge them, we don't actually have to go update all of the labels for all of them, because they all point to the same place. We just have to update that place. There's two addresses, one for this side and one for this side. We just have to update one or the other of those to be the same as the other one. And then you can recursively do this. So the trick is you make each node point to some other node. And they keep pointing to each other, and it forms a tree, or really a forest, because you have multiple disconnected ones, where the tree, you're only storing the parent pointers. You're not storing the downward pointers, just the upward pointers. And to find out which region you're in, you follow all of the parents up, which is what I was doing here with leader. Instead of parent, I called them leader. Should probably call them parent. But now, if you do that, you can really efficiently, it's called union, but you can't call it union, so I always call it onion. So we're going to, let's name them 2 and 1 instead of 0 and 2. That's really dumb. So when you want to, what you're doing here is you're saying these two are connected. Now, if they're already connected, you don't need to do anything. But if they're disconnected, you want them to become connected. So we say P equals find x1, y1, point Q equals find of x2, y2. And now we have the leaders, all the way up the parent hierarchy, leaders for both of them. So if they're the same, we don't have to do anything. They are already in the same thing. Somebody tried to combine them. If they're not the same, we just want to make one of them point to the other one. So we can say leader of p.y, p.x equals leader equals q. You just pointed it directly at Q. Now, this is one of the 2 things that you have to do to this, the naive version of this algorithm. I've just written the naive version. It may be broken, but that's the naive version of this algorithm. This does not get you all the way to the inverse Ackermann function performance. There's 2 things you have to do. One is called path compression, and the other one I don't remember what it's called, but it's deciding whether to use P or Q here. If you make P point to Q or make Q point to P, and if you pick the right one, you can make it efficient. You want to do whichever one is shallower. But I don't actually know how you know which one is shallower. I've never bothered implementing it, so I didn't even know. But we will implement path compression. Path compression says when we walk up this tree, we're walking up the parent pointers. Let's go ahead, all of the ones that we visited, so this is totally unchanged. I'd forgotten to declare P before. So this is just the same as it was. When we finish the recursion, we get all the way back to here, we find out who the real leader of X and Y is. Let's go ahead and update that to point to the real leader. That's called path compression. And I believe with just path compression, that gets us to log star. So it's n log star n, which I don't even remember what log star is. Maybe it's log repeated that many times. I don't know. Or how many logs do you have to, yeah, something weird. So this is enough for us to find all the leaders everywhere. So all we have to do is loop over everything and make all the connections. So we go for j equals 0, j less than h, for I equals 0, I less than w, if map of, it's annoying because it's not 2D, it's 255. I could threshold here, right? I could say greater than equal to 128. Maybe that would be smarter. So if it's open, we're making white be open. Then what do? I check if its neighbors are open. So let's do this in a slightly different way. Hard code it again. So this will be image. This will be map. Let's go ahead and let's just be lazy. Okay, we're going to make this version. We'll make the library more robust, but make this version assume that the border is opaque. So we can always test. So we can say, let's look up, and if that's also open, then we onion I, j minus 1. And I'm going to put these all in one line because they're all going to have a pattern. We will look down, and I type with that. And then we're going to have +1 and -1. And I'll just go ahead and leave these with kind of a dumb alignment. +1, -1, make sure this match. Plus, then minus. Plus, then minus. Okay. And then we need to initialize it. So because these aren't symmetric, everybody put a nothing's prefix if you talk to me so that I can see it, because I'm just going to glance over when I get in the zone here on programming. So I just need to initialize. So we have leader of j of I dot x equals I and y equals j. And let's go ahead and fully brace that to keep you all happy. All right. So in theory, once I've done this, what I can do is go through, and now I want to assign them colors. And so let's just go ahead and let's cache inefficient. So this isn't a great performance thing, but I'm going to assume we're not going to run out of that. So then we say if leader of j of I dot x equals I and leader j of I dot y equals j, then it points to itself, which means it's the leader of its group. It didn't get pointed to someone else, so it gets assigned a color. What did I call it? Color. Color of j of I equals C++. Uh-oh, I used C++ in this. We'll leave 0 for everything else. And then we make another pass through. And we color everything that was not pointing to itself with the color of its leader. So now, how can this perform the way I said? When these finds, it's building this tree, and it's you're traversing up this tree, and look at this. Every single one, I'm going to traverse off the tree at every single pixel. So how is that not like log n? And the answer is that path compression is squeezing, so any common branches get shortened down so that performance find, is it just I, j? Yeah. Oh yeah, that's a point. And then we copy over the color from the leader. And there we go. So if I don't have any bugs at this point, we can write out that color. I guess I want to use image right, since I don't have any way easily to display an image. In which case these want to actually be colors. Let's just make it 32-bit. And color, how do I update the color that's an interesting way? Let's see, times equals. And then let's orient, keep it from being too dark. Let's do that. Because we want the blacks to stay blacks, so we'll do that. And make it opaque. Wait, RGBA, opaque goes at the top. So I should be able to multiply the color. Because of the compression, the maximum path depths will be the number of partitions. No. So you can get a worst case where you like sort of visit everything in the wrong order and your path is like the entire size of the component for one path. But once you run a find on that one, it'll flatten that whole path down, which only takes order n time. Worst case, the whole image is one thing. And now it's compressed and nothing else takes time. So it's an amortized algorithm. An amortized algorithm is one where basically someone has done a proof and showed that any sequence of operations still always will. No single operation is guaranteed to be this fast, but any sequence of operations is guaranteed to have an average time that meets that thing. So you might hit a single find operation that's really slow, but that can only happen if everything else was fast enough that the whole thing works out. So I should just be able to multiply this by some number, but I don't know what number I need to multiply it by. I guess I want a... I guess what I actually want is STB rand LCG, which is just a multiply like that. Rand LCG, I don't know what's called. Let's just look for LCG. Rand, of course. I mean, I could use any rand, I guess, at this point. And then we want to say STB image right PNG. Is that how that's done? Darn it, why am I not getting my completions? Oh, because I haven't compiled. Why does this conflict? What? I definitely use these in the same thing at the same time. I definitely compile both of these in my test thing. How can these conflict? What the fuck? That's really weird. Oh, this is an old version. Haha. Purge. What is this called? Quick. Copy. Sean. Purge. STB. STB image right.h. Oops. Now let's come on. All right, there we go. Leader. What? Oh. That's supposed to be a recursion. Nobody complained about that. How was it? I was talking about being recursive and it wasn't recursive. Doesn't seem like you should have to search all four directions, just the positive ones. Yes, you're right. Also seems to be missing the corners. Yeah, I'm intentionally saying that the left edge and the bottom edge are always a solid. All the edges, so that I don't have to range check those off the edge. So the proposal here is that I probably don't have to do this. Although then I might have to change how far my loop goes. But who cares? Close enough. Let's make that change after we verify it works at all. Okay, good. So now do I get my complete for this? Dang it. Well, at least it knows about it now. No, it doesn't. What? What is going on here? Right, PNG. Oh, all right. That's why. God. All right. X, connected components, .png. WH comp data. WH components data. Stride in bytes. All right. What are the odds this works? I say very low. Okay, that's a pretty long time. What are the video lagging behind the audio? Is the audio still working at this moment? Yeah, my video stopped updating as well. Let me know if it's working at all or not. Should I drop my quality at my end? You're not seeing drops. Okay, great. Then I will show whether this worked or not. No, it's called connected. Probably not. I mean, the green is all correct, but the black is all wrong. Oh, I didn't initialize the memory? No, it's constant. It should be black. Let's bring it up again. And then bring up the... Alright, so what can we see here? Well, we do have a constant color for this eyebrow shape, and it's like connected a little bit here, and that all looks correct. So this all looks like it might be correct except for the black regions. Oh, which are all their own leaders. They're all single element leaders. So this is actually 100% correct. I just need to suppress them, I guess. If map of j times w plus I does not equals 255, then we assign a color. All right. And let's try running a release build, since that took forever. Okay, it's not so bad. There we go. Oh, it's transparent. C equals... Yeah, we got rid of this set. C, this is dead. C equals opaque, black. And then this is C, equals C. All right, one last time, and I think we're done the setup here. All right. Seems pretty reasonable. Let's look at the thing again. So, yeah, I mean, it's not real image segmentation, right? This is of a binary image. Like, image segmentation is on a, typically on a color image, and you're doing real complicated stuff. Like, this is really easy. This is a really easy version. So, yeah, I'd say that worked. I didn't have to fix any bugs other than the display bugs. The algorithm itself seems to work. Now, the question is, how fast is it? What's the easiest way I can measure time accurately? I guess it's this way. Release quick. Is that the right thing? Oops, timer. That's not very fast. That includes loading it, though. That's probably pretty fast, too. And includes writing it. All right, so what's our high precision timer? Query performance counter? Is that right? I wish there was an intermediate. I misspelled performance. Oh, and I hit the lock up my IDE button. Query performance counter. I wish there was a simpler thing. Query performance counter, large integer, start end. Query performance frequency. And then what? See, these days I like use FCL, so I don't worry about remembering these things. So then I have to divide those somehow. I don't want the quad part. I want the... Where's the large integer type? It doesn't have a link to the large integer type. Come on. All right. Okay, quad part is the... it's the other way around, and dot quad part. Why did I not? Wait. Oh, because I have to capitalize it for it to... So then let's just start a new scope here. Double TM printf time percent 6.4 LF milliseconds TM times 1000. I have to actually include Windows. I have to do that before include stb.h. Okay. So it takes 100 milliseconds. So if Nick Mining is still around, there you go. There's the dumb version of this. Oh, somebody explained how to do it in chat. So, and this is kind of in an inefficient thing because I have two things. So a thing that does a full pass over the 1K by 1K, and I'm not packing the map. The map could be packed down to 1 bit instead of 1 byte. I don't know that this can be packed there very much, but, and this is on a relatively fast computer, but with a slow compiler, it doesn't produce the best performance. So first of all, yeah, like here, I'll put this on, I'll just put the whole file on just, in case somebody wants to try using this algorithm, but it's obviously not been libraryified, right? It's all hard-coded. It's got these hard-coded sizes, even though it loads an image of any size, but then that is hard-coded. But, you know, there's the starting point. So now what we want to do is do a totally different way. So this algorithm keeps finding merging connected components. It happens to walk through in scan order, but you could walk through the whole map in random order and it would still produce the same result. It would actually have like different internal paths as it's building it, but then this final flatten step would just flatten it all out to the same thing. And so one thing that means is that if you have a dynamic map that things are changing, like in Dwarf Fortress, and you add a new connection, if you just maintain this data structure, you can join dynamically because you added a new connection and have a new updated set of connected components that you can use to accelerate that whole, is this pathfind even possible? But if you break a connection, I started to talk about this before, I think. Remember I talked about that trick where in some sense you're pointing everything pointing at a label instead of storing a label. When you split the components, the problem is that you have this big map. You have this big map and you split this here. You know, if the way you built it was in some other order, so like say, you know, had this component, like say all of this was connected and then this was another object and these got merged somewhere like here. If you split here, there's no guarantee that these are all pointing to one area and these are all pointing to another area and you can update them efficiently. Instead, no, you have to go over all of one side or the other and update their components, which is really not efficient. Worst case, we have a map like, oh, and it is worth keeping in mind, Nick, that this map may not be very representative of your maps, right? This is going to be potentially data dependent. Hopefully not very data dependent. Hopefully as long as most of the map is open, which I guess this is a little bit, there's a lot of closed space here, so it might be a little bit biased. So we need some kind of totally different strategy if we want to be able to incrementally update this and not just merge things together, but be able to split them. And I looked at research on this and didn't find anything. I'm sure it's out there. So I think it's unavoidable. I think there's this hard problem that it's kind of unavoidable that you have to essentially rebuild it from scratch in some sense. But there's a trick, a totally different kind of trick that we can do. If we take this image, and where's my Photoshop gone? If we take this image, and we split it up into pieces, let's make them a bit bigger than that. Let's make it really exaggerated to make it clear. If we split this map up into all these pieces and leave them as pieces, then what we can do is find within each cell, we can find all the connected components independently. And their connectivity across the edges. Then basically we have all these little pieces, and we make all those pieces be nodes in a graph and run a find union disjoint set forced on those pieces. That we can do much more efficiently because the number of pieces is much smaller. Like here I have 16 by 16, right? No, 32 by 32. Yeah, so these are 16 by 16. So I have 256 things here. Each one might have multiple pieces in it that I have to process. So I have maybe 1,000 pieces here that I would have to run the full disjoint set forced on instead of the million that I have in the other thing with the k by k. I think that strategy, and now you have to incrementally update the little pieces, but you only need to like if you add a connection somewhere, you only need to incrementally update this little thing, and then you run the full algorithm on the whole, on all the big pieces instead of on every single node. So that's the overall strategy that I think is going to work, but I've never actually, I started to implement it, I've never gotten it all the way going and like measure the performance, so I don't actually know that it'll work. There's some complexities due to memory management that I'm not sure what we're going to do about. And I should make some, let's just save this SO2. I wanted to check whether the maps that I made for the herringbone wing tile, if they are k by k. This one, and then this one. And then let's scroll down. Oh, these are all been fat bitted. No, they're smaller than that. Yeah. So if I had that stuff set up, I could generate a big herringbone wing tile map and then break it up so it's not fully connected. But I think what I'll do instead is I'll just make some sort of obvious test maps. So what do I want to do here? Oops, I'm in the wrong window. So let's pencil. So what we're going to do is let's have a little, this is inverted from how I want it to be. So I'll invert it in a second. All right, so here we have this, and then what we're going to do is we're going to add a new color. And this is the color that we're going to update. We'll like one at a time, we'll update these. And then let's actually go ahead and invert it. And then let's make the amount that we have to update much smaller, just so we don't waste time. Okay, so that should still be connected if we do this. Make it slightly more aesthetically pleasing for no good reason, totally wasting your time on the stream here. But personal satisfaction is important. And actually, we'll do that. All right. So all of these will need to get updated, and we'll do them one at a time, and one of the ones that we'll update there will actually break the connection and cause everything to disconnect. And it might disconnect one side off first. We'll see. All right, so that's a test map. What would be another good test map? I guess I could use one of those herringbone wing tile maps. It doesn't matter, it's been fat bitted. Oh, that. Copy image. Let's save this as map number 3. So I saved to the new name first before I change it so that I don't forget and accidentally overwrite the old one. We want a nearest neighbor resample. This isn't got nearest neighbor. Well, we'll just threshold it. Wait, there must be a threshold. I should learn this. Image adjustments, threshold. Okay. And then what we'll do is we'll just randomly update pixels and eventually it'll disconnect probably. So I don't need to fully disconnect everything. I just want, oh, that, yeah, that's still connected. I just want it to not take as long to disconnect everything. Oh, that's maybe too much. All right. Oops. All right, so there's 3 maps. Who knows? It gives us something to play with. My chat has not updated in a while. I just want to check it's actually still running. So let's move this now into the reference implementation. Star map width and height. Okay, thank you. And put that up here. Okay, so this reference implementation, super dumb, super hard-coded, whatever. Now we'll start writing the real implementation, and I'm just going to go ahead and start writing it in STB style. I'm not going to like try to get the algorithm working first and then modularize it back to STB style. So, but what I do is I just do it inline, and then I'll split it out to a header file later. So, so I don't bother doing like the header file section first. So what do we want to do? What we need. Okay, so I'm going to stop talking to myself as much now, so I can actually think about things. I was just asking chat something, trying to think about how I want to do memory management for this. So we're going to need a structure that's going to contain our state. So let's go ahead and make this. We'll leave open the possibility. No, let's not leave open the possibility. Well, someday we may make 3D grids and even regular graphs that aren't on grids, and they'll use a different structure, and they can have 3D or whatever tacked onto the name. Grid we'll assume is 2D. 3D can be a voxel or whatever. All right, so what do we need to store? We need to store the map. So we need width and height. So another option would be, because this is used for game-like things typically, was we could hard-code in the size. It's an H file, so you could define the size before you include it, and it could be hard-coded. And that would let us use constant for the strides, for the array, for the 2D array lookups. That could all be, the compiler could have constants for that. And we could require them to be shifts instead of multiplies. So, like that's, since the concern here is performance, I think that's actually worth doing. So, and if you need multiple grid sizes, you can include the thing more than once with each size. And if you need dynamic sizes, you're fucked. I think since the goal here is performance, that's the right trade-off. If you don't care about performance, you can do it the naive way. So let's try it that way, at least to start with. So log 2 is going to start as 10. X log 2 is 10. So then, CC grid Y is 1 shift left. STD CC grid. It should be size. I'm trying to not use size anymore if it's a count. I'm trying to use count. It's hard to remember to do that. And then size is for things that are like bytes. So grid count Y log 2 and X is of course X log 2, and X should come before Y. So now we can say Y map. So let's call this map stride. So this is how many bytes we need per row, and that is 1 shift left STBCC grid count X log 2 minus, we can fit 8 per byte because we're going to use 1 bit for this. So we do that, right? So if this was 10, we're trying to fit 1K things. 10 minus 3 is 7. It becomes 128 when we shift. So 128 bytes can store 1K bits. So I think this is reasonable. So now our grid will still allow you to have more than one of these. Maybe you have 2 floors, right? Or something like that. So we'll go ahead and put this, but we're going to go ahead and make the whole grid, the whole data structure stored in the grid rather than indirected. Sure. And then there's no mallocs except for the grid. So sure, why not? Whatever. Like, we can change this if people don't like it. So UN8 map, STBCC map stride. That's the horizontal, and the vertical is grid count Y. So for 1K by 1K, that is 1K by 128, is 128 kilobytes. Does that make sense? Let's type it. Does that sound right? 1K by 1K is 1,000,000 pixels. So it's 4 megabytes if it's the color. So sure, I think that sounds correct. Okay. Then we need the clusters. That's what I'm going to call them. These should be double underscored. They're internal. So the cluster count X log 2. Actually, you should be able to override it because performance could change depending on what you do. So now, cluster count X. Oh, so much boilerplate. Cluster count X log 2. Oops. And the same for Y. And so I wanted to check how long it had been when I started this. So maybe 45 minutes in when I finally actually started working on the lib. All right. And then cluster, well, in this case, we'll call it size. So this is one shift. Let's just cut and paste this. So total size of the grid minus the number of clusters is how big each cluster is. Okay. So what do we need to store? Okay, and then we have what we're going to call clumps. So how many clumps can we have? Well, so the worst case is 32 by 16 in the cluster, but most of those will only be connected to themselves, right? This is if you do this is this pattern. This has 50% occupancy. So we could consider, to save memory, that we wouldn't use if we could just have a whole bunch of memory that we reserve but don't use unless you hit this case. If we don't even want to reserve that memory, we could try to look for we could make it that if it's only one large, it never uses the memory. And so then the question becomes, what's the worst case you can do with that? That one option would be this. Then these don't use any memory, but these do. So, come on, copy both. And that would use 2/3 of every other line, which would be 2/3 over 2. So that's smaller. That's only 33% occupancy. Oh, well, that's 33% occupancy. Okay, right. This is if I don't make the, if I don't apply the rule, try to optimize those. This is more than 33% occupancy. Wait, what is this? It's 1, 2. So on half the rows, it's 2/3 full. It's using 2/3. Wait, no, it's how many clusters are there? So on half the rows, there's 1/3, and on the other half, there's 1/3. So it's just 1/3. Yeah, okay, it's 33% occupancy. I did the math wrong, but it got the right answer. And then the other option would be to like double up all of them. So, right, the whole point is I have to make sure they don't connect. Any pattern that connects reduces the number of components. So I'm just trying to find what's the worst case when they don't connect. Okay, and so that the number of clusters on each row is 25%. So 33% is probably the worst you can get. Okay, so then if I did a rule where you didn't use it, one by one, don't hit it, you could still hit 25%. So if I tried to be smart, I could cut my memory for this element of it in half. But PCs have a lot of memory, so let's not bother. So worst case number of clumps per cluster. Let's just call it that. That is one shift left, SBCC cluster count. No, we don't have a name for it. SB cluster size X. In fact, actually, we should make cluster size be the one you pass in, which is also 5 though, because of how that works. and then this one should be double underscored, and it's SVCC grid count x log 2 minus cluster size x log 2. Still nobody has any questions. All right. Boring boilerplate. And then this now becomes SVCC cluster size x log 2. And this becomes y. All right. So we can have this many cluster size x log 2 plus SVCC cluster, oh, this is not double underscored anymore, size x y log 2. So that's the size of a cluster. And we can have 50%, so let's subtract 1. That gives us some max clumps for cluster. Then the max clumps that we can have is, of course, SVCC max clumps per cluster times SVCC cluster count x times SVCC cluster count y. And then we need a struct with whatever info we need for a clump. What info do we need for a clump? Well, we need to know for a given clump what other clumps it connects to in adjacent clusters. It doesn't connect to any clumps in the same cluster because they'd be merged. We also need to know which grid squares it's made up of. But eventually, we're going to have a function that says, given these two map tiles, map grid squares, are they connected? And to answer that, we're going to have to look up which clump each one is in. And then for each clump, look up which connected components it's in. So we're going to have to store that mapping from grid square to clump. There might be ways to save memory on that too, but anyway, if we have stored that, then the clump doesn't need to store necessarily the list of all the things that it's involved. We can just search through the cell and find them all if for some reason we need that. So let's go ahead and have that. So I think the clump ID needs to be let's see, unit 16, and I can't use these types in this unsigned short. And this is an unsigned char. So SVCC clump ID clump SVCC grid underscore grid count y SVCC grid count x. And then we'll have clumps. Clumps. SVCC max clumps. And let's call this clump, and let's call this clump for node. So void SV or int SVCC grid nodes connected. And then we say grid, and then we say x1 int y1 int x2 int y2, and we say SVCC clump ID, C1 equals grid clump for node, y1 x1 VCC clump ID C2 equals gr clump for clump for node y2 x2, and then if clump of C1 dot leader equals clump of C2 dot leader, then that's true. So we just return that. And that could actually, we could implement that as a find union kind of operation as well, rather than assuming that that's all flattened. But we might just flatten it all up front so that this can be faster because it doesn't even have to test. Okay, so the clump needs a leader, and we need an out of band value, which I guess will just be SBCC max clumps. So typedef unsigned char 5 max clump. Let's, yeah, okay. It's SBCC max clumps. So we want to use that as an out of band value. So that has to be within the maximum expressible thing, which is size of is in bytes. So you want to say 1 shift left 8 times size of SBCC clump ID. So I'm doing a compiler assert here, and I don't have a macro for compiler asserts. So for example, if this is 2, and this becomes 8 times 2, which becomes 1 shift left. So this won't work if this gets up to being 32. So like if clump ID were 4, this isn't going to work. So that's kind of a problem. Maybe I need max clumps log 2 so that I can do this math in the log 2 version. Let's just assume it has to be 16-bit, which, by the way, isn't enough. For the 1K by 1K map, you could have more than 64K. So let's just do this. If so, in fact, this is going to break because this is not going to fit. The max clumps that we're currently doing, run calc, is max clumps for, it's just 1K times 1K over 2. So yeah, that doesn't fit in 16-bit. So this has to be an unsigned int. That's unfortunate. So that becomes a lot bigger. So that becomes bigger. So the map is 1 bit per thing, but this is 4 bytes per thing. So this is 4 megabytes now, even though this is much smaller. So this could be a caching issues. It's totally possible that we would actually always be limited to 64K clumps, that you would never make a map that had more than 64K clumps. Because as soon as you disconnect stuff on your map, you can't get to it anymore. So it's like pretty unlikely. So it might be nice if we could require that, but I don't know how to enforce it. So we're just going to have to pay that price. We could cut this in half with a little sneaky trick. We only need the clump for node every other tile, because if 2 tiles are both open, then they both must have the same cluster. So you could literally just only store every other one. Can't do that in both dimensions. Can't cut it down by a factor of 4 because of that diagonal case. So now this is... so this is currently 1K by 4. It's 4 megabytes. This is currently 1K by 0.5K by, at the moment, 4. It will get bigger. It's just 2 megabytes. Okay, what else do we need to know about a clump? We need to know about all of its connections to adjacent clumps. How many connections could you have in the worst case? Well, you could have a clump that that on the edge of the tile is like this, you know, that's fully connected internally. I'll just let it be an odd size for simplicity just to show this. So if we had this, this is why the whole worst case thing is really problematic. I'm trying to use a fixed amount of memory. It's like terrible. Like this might just blow up. I might have to actually switch this to being malloc, or just some kind of finite bounce. So these could all connect to unique separate chunks. So like the next chunk over could have these as its clumps. And that all extend all the way up to the top of the top of that cluster. Clusters. Right, these could be the adjacent ones. And they might be connected or they might not, right? Like that's sort of the intentional thing. Like if these are connected within the same chunk, then I don't actually have to track these independently. I just have to know that there's one connection to this clump. But if they're split, that's a clump and that's a clump, I have to keep track of those independently. So the worst case number of clumps you could have is circumference over 2. And circumference is cluster size x plus STBC cluster size y times 2. That's the circumference. And then it's over 2 because it can only be every other one. So it works out to that. Worst case, you could have that for every clump. But you can only have that per clump if there are no other clumps out, right? So this is actually the worst case per cluster. So if we don't pre-allocate this to every cluster, if we don't have every cluster store the max, well, if we have every cluster store the max, if we have every clump store the max exits per clump is SBCC cluster size X plus SBCC cluster size Y. If we stored that for every clump, right, then cluster size X is currently 32. This would be 64. If we stored that for every clump, how many clumps do we have? Max clumps, 2, no, wait, it's that. 512K. So it's 2 to the 19, right? Then that's times 2 to the 6. So that gives us 2 to the 25 exits. And if we need to store clump IDs for the exits, which is what we'd need, those would be 4 bytes. That would take 27. Is 128 megabytes. Oh, good. That is an old quote. So corners can have 2 connections. Good point. You are totally correct. So I think you can only be in 2 corners and still trigger that, but only 2 corners can trigger that. Only 1 corner can trigger that? Like, because the odd even thing basically means that if you actually, like, if we look at a 4x4, the worst case that you can do. In fact, actually, it's hard to because you have to connect into the middle. So I'm trying to think what the worst I can do is, and have separate connections. See, if I do that, then this is all actually one solid connection. Right, and so then I can connect 1, 2, 3, 4, 5, and then 6, 7. So it's 4 by 4, and I can still only get 7 connections. So I'm not sure. I think because of that odd-even principle, it may not be possible to get. Right, see, if I try to connect that way, I've turned this whole thing into a solid connection. So I think it may not actually be possible. So I'm going to make the assumption that this is true, and we can test that. We can add an assert, although we probably won't ever have test data that does it, but we can try to see if we can do it. So, yeah, I mean, I probably should document what clumps versus clusters are. There we go. So clumps are always still within clusters. Then we will find the connected components out of the clumps. So here, this is a cluster, and it happens to have one clump in it. This cluster has 4 clumps in it. This cluster has 5 clumps in it. So I think you can't do it. I think you can't exceed that because of the odd-even problem. But I don't know for sure. And actually, the assert probably isn't good enough because I have to actually do some thorough checking to find the test case. So maybe the better thing to do is pad this up by 1 or 2. Because the worst case is definitely only getting it in... No. Right, the odd-even problem isn't the problem, it's the connectivity problem. Or the odd-even problem was this, that... Let's just... Let me put dots down to show where the spaces are. The odd-even problem is this. If I want the clump to be connected, it's hard to have... What you want to do is you start with this pattern, right? The maximum number of clumps, and then you connect them. But the problem is I still haven't connected these corners. So if you just do this, if you pretend I could connect them all, I would still only have 2 extra connections, 1 for each corner. But it turns out then you need to actually connect these up to each other. I could do that. Again, that steals that connection here. And then connect this one. I can either connect here or I can connect here. And either way, so yeah, it looks to me like you just can't, at least on the 4x4 case. But it's a totally valid point. I was totally wrong. I had made that assumption in a bogus way. I think it turns out to be true, but my logic, I had not done any logic to prove that. I had not thought it through. But I think it does turn out to be true. We're just going to assume it and assert. And if it turns out I'm wrong, oh well. Because this lets us keep it as power of 2 in case we wanted to go back to log 2s at some point in here. These are all still powers of 2. But anyway, so as I said, this uses 128 megabytes if we fix allocate it. And it's not going to actually use that in practice. So what we're going to end up with are these clumps with all this memory being used. All right, we'd have this adjacent clumps. You know what would be really nice is if we could have a max of 256 clumps per cluster. That would really simplify our lives, because we could pack them into 8 bits for which cluster it is, which clump it is. What about if we did this? Unsigned short clump index. We need 4 bits. Okay. Signed short clump cluster dx to signed short cluster dy to relative clump ID. So this is, we know all the connections must be to adjacent clumps. In fact, they actually have to be 4. Since we don't allow diagonal connections, there's only 4 possibilities. So we could actually do this better. This could be 14, but let's just do it like this for now. Okay, this would be 2 bytes now, so that brings us down to 64. So anyway, so we could do this. It'll take 64 megabytes. This thing in this particular configuration, right, we could definitely try changing how the cluster sizes are. But I think these all multiply. Well, the circumference one definitely would change. We actually want it to be bigger. That makes the circumference versus area better. Max exits per clump. So bit fields can be sign extended, sure. I mean, I don't normally wouldn't put signed. I'm just doing it here to be explicit about that. I mean, it may produce really inefficient code. Like, I may be better off with a little table of what the dxdy is and have 2 bits of direction. So I now have to have some more logic to go. Oh, right. So what I was saying is, now if the max exits per clump is currently 32 plus 32 is 64. This is 2 bytes. This is 128 bytes plus a little bit more. So it's going to be more than 2 cache lines. Most of it will be unused most of the time. That's the problem. We're really wasting a ton of memory, a ton of cache on this data structure for the worst case, and we'd have to store count, obviously. Num adjacent. Oh, this is just called clumps. Without saying connected, it's implicit. So the question is, if we don't do this, if we want to store a variable length list for each one, we kind of need malloc. We can do it ourselves, but we have to make a big pool that we memory manage exactly like malloc. And games don't like using malloc, right? But this is super inefficient if we don't use malloc. We need something malloc-like, or we need it to be really inefficient cache usage. So I don't know. It's a hard problem, right? I probably don't really want this structure to be 128 megabytes or 64 megabytes. I guess I got it down to with that. Oh yeah, and I said I could shrink this one down, but this one is so much bigger. That's a bit more. This one is so much bigger that who cares about shrinking this one down for now. So that's doing worst case. It's pretty gross. Well, let's stick with it for now. We can always change it. So I don't think I can get that smaller. I could get down to 8 bits to get down to 8 bits, this could be 2 bits and this would be 6 bits. So I'd have to restrict you to most 64 clumps per thing, which is actually in the real world totally sane, right? A 32 by 32 thing having 64 separate disconnected components is pretty much the limit. So like you could certainly imagine something where the efficient algorithm assumes the 64 limit, and then it has some fallback path that it does to deal with chunks that have more than 64 clumps. But it's a mess because the adjacent ones need to know about it and all that stuff. So I'd love to do that. In practice, you're almost never going to have 64 clumps per cluster. It's really hard to do. Right? You have to have the checkerboard pattern. And most games you wouldn't build that kind of, I mean, I guess you could, right? In a Warcrafty kind of game, you can, or StarCraft, you can place down your stuff in this terrible pattern that blocks things off. I don't know, StarCraft might have fixed that to avoid that, but in Warcraft you definitely could strand people. So you could put things down in a checkerboard pattern in Warcraft, and it would only be in one place that you would have this terrible clumping, probably where you were building. You wouldn't have it over the whole map, because you just can't build over the whole map that way. So, I mean, I bet there's something you could do here, but enough of doing this. At this point, the algorithm writes itself, right? Like, hey, it's all pretty clear. No, that's not true at all. You have no idea what I'm talking about. So, we're going to let the user allocate the memory for it, since we went with the static approach here. So we'll take an STV CC grid, and we'll take an unsigned char map, and we'll take a width and a height so that you can dynamically size it smaller than the max size that's been propagated here. Here it is. Int with height. Let's put this first, just because. Although I usually do buffer inlet size. Okay. And then let's threshold. Let's pass in a threshold. No, let's make you do it. So what do? First we pack our map. If map of I plus k times j times w plus I plus k greater than equal to 128, then grid greater than c or equals 1 shift level k, and then we say map, it's a g arrow map of I shift level 3 j equals c. All right, we copied out the map. Now we need to initialize the clumps. So we go over the clusters. We don't have any cluster tables yet. We'll have to add that. Max clusters. What did this turn out to be? Oh, it's only -1. Yeah, that's huge. Also, this is going to be another big data structure. That's always going to fit in a. You'd have to have 128 by 128. You could do it, but 128 by 128 is so big. I think did I ever do the... I didn't actually do what I want to do here. Didn't finish this. If that's true, that's 1, otherwise it's -1. Max exits. Max exits per clump has to be less than equal to 256. All right. Yeah, so the thing is I'm doing this both top down and bottom up, so it can be pretty hard to understand what I'm doing. So each cluster, we need to store all of the clumps that are in it. And our max clumps, I said, was per cluster is this. So it's pretty big. So it has to be a short. Num clumps. And clump SVCC max clumps per cluster. So let's, rather than store them in a big global table, we're storing them locally per cluster so that the adjacent clump stuff can work. And these both need underscores. Okay. And now we have to store clusters. And that's SVC cluster count y. SVC cluster count x. Okay, how long have I been going? 1:30. So about 45 minutes on this, and this is all I've gotten so far. But hey, it's getting along. It's this the data structures. I wasn't joking when I said it writes itself. I was joking and I wasn't joking. Once I get all the data structures, the algorithms needed to do this are pretty obvious. And that's why I was saying it's a mix of bottom up and top down. So there's two things we're going to have to do. We're going to have to find the initial state, and we're going to have to do the updating. And some of that logic will be shared. So let's just go ahead and do some of this just to get some code in. So one of the things we want to know, what we want to do is build clump for clumps for cluster. So assume we have no clump info. So what we need to do is do a connected components within the cluster. So for that, we can copy this algorithm. And then we need SVCC tiny point leader. And this will be cluster size y, SVCC cluster size x. If it's 16 by 16, that would be a byte. If it's 32 by 32. Okay, so that, how big is that? Is 1k items times 2 bytes. So it's 2 kilobytes that I'm allocating on the stack. That's not too bad. And then we will assign them clump IDs. So in fact, this can be this clump ID. Who's using it? It's always within the same clump, right? So we can have clump ID. We've changed clump ID. Now clump ID is going to be short blankly, and it's max clumps per cluster. Now, we're only going to make the clump ID be defined within a cluster. So, clump ID leader relative clump ID to the adjacent clumps. Okay. Yeah, and I don't know that this is enough data to do everything yet, but so we want to build the clump. So right, so we had the leader and we had the color. So the color has to turn into a clump ID. So let's go ahead and rename this one to parent, and let's rename this one to label. Cluster size Y, BCC, cluster size X, and we need an out of band value still. Is this the one that we made sure had an out of band value? Less than, yeah. So that we can flag opaque tiles. So, SBCC tiny point. Oh, I never verified that I only need to do... I didn't save that. That's too bad. Let's see if we can actually still use it. I didn't verify that I could comment out two of the lines up here, right? We said two of them were redundant. Somebody in chat pointed out that two of them were redundant. So what was that called? Reference. So let's see if that still works. Yep. Okay. Okay, that still seems to work. And then now let's try taking out those two lines. Let's only go positive direction. Don't know if it'll be any faster. Hello, where is it? All right, that's at the other end. Hey, look, it's twice as fast. It's interesting that it's twice as fast. So the color is different just because I did things in a different order, but it looks correct. Let me, since Nick has not been commenting in chat, let me message him to make sure he knows about that. Okay. So that's good to know. That's 50 milliseconds. It's not bad. If this were something that you could do in the background, do every once in a while, do it once a second. You know, because your AI maybe is already running pathfinding in the background because you're pathfinding on big maps. And it's okay if once in a while it runs a long pathfind that totally fails because the connected components hadn't got updated yet. You could definitely make that work. 50 milliseconds is not bad. I mean, this is a fast-ish computer. But what we're hoping is that this new algorithm is going to be much faster. I don't know if it will be. I have no idea. I've never implemented it. I've just thought about it. I've thought about it a lot, which is why I can, why I understand it in sort of a deep way already. Log 2 undefined. Oh, I lost an underscore. Cluster size, cluster count, cluster count, cluster count. Okay. These are G arrow clump. So yeah, these actually have to be changed. So what we need to do is say define stbcc cluster for cluster x for coord x. X is x shift right cc cluster size x log 2. Let's go ahead and call that y. Just speak up. So let's see. So now, because these are all relative things, this tells us the clump ID within its cluster. So we still have to actually get the clusters. And because I'm lazy, I'm going to use the same variables again instead of defining a new set, because I don't have to name them actually. It's not so much declaring them as I need a new set of names. I'd have to call them cx1. So let's just overwrite them. Maybe it's bad. I don't know. I don't care. That's how I write code. Oops. All right. So now we have the clusters. So we can say grl cluster y2 x2. Well, let's do y1 x1 dot clump of c1 dot leader. Okay, it's still valid. Now, one thing I'm missing is I have that out of bound value. 2 leader. So I need to actually do that. Handle the out of bound value. So, I changed it from leader, didn't I? Oh no, I did call it leader still. But because it's clumps, these don't really need to be. These need to be clump IDs, but leader doesn't need to be clump ID. This can just be. Yeah, and this needs to be global, not local. So, did we say that was max was short? No. Inside int label. So let's do it like this. Label 1, label 2. Label 1, oops. Label 2. Oops, label. Now, let's go ahead and just say that if we set label to 0, these are definitely connected. However, if either of them is 0, right, okay, yeah, let's just do it like this. It's clear. If either is 0, then they're not connected. That's how we handle a wall query. Now, the normal game scenario would never query with the wall. It would never try to pathfind to the wall. So this is wasted code, but given the amount of other stuff we're doing, it's totally fine. If you never call it with that case, this will always branch predict correctly, and it's all fine. All right. What font am I using in the command? It's just the default, I think. Raster fonts. It doesn't even have a name. 10 by 20. Because I think they're bitmap fonts, so the size matters. All right, so build clumps for cluster. We changed this. No, wait, for this, we do want it to be labeled. It's a local. This is just local. So we're going to have a SBC tiny point, SBCC in cluster find. And then we'll have a SBCC in cluster union. These are static. Okay, so here's our little find union. We still need to actually change the code. So this needs to find. We need to pass this structure in. So let's do a type abstract actually of this BCC cluster search. So cluster, what do you call it? It's not a search, it's a, you're finding the connected components. What is that? What is the noun of that? You're not searching, you're grouping, you're clustering, except I already am using cluster. Whatever, placeholder. All right, so you're building cluster build info. All right, so we'll have to pass this in. Cluster build info, CBI. So this is STBCC tiny point equals CBI parent Q equals STBCC. Whoops. STBCC cluster find CBI parent. Voila. And then this one also needs to take SBCC cluster build info CBI. Type out label 2 equals line. I don't even know what. Oh, label 2. Yep, correct. Thank you. And this takes CBI. Let's take CBI, and then this is CBI. Sorry about that. The fuse blew. It's been happening to me like every other day or so. I assume it has something to do with the construction that's happening outside on my building. I assume they are somehow triggering it with something they're doing. I reflexively hit Control S really often, so I suspect I'll have lost 4 characters or so, and I don't even know how much of that got out on the stream. So I just fixed that, and then I'd come back down to that. All right. So it wasn't the fuse blew, a fuse blew. Did I say the fuse? I think I said a fuse. I meant to say a fuse. All right, so now that, can you quote that? So cluster build info, CBI. And then what we're going to do is we got to initialize it. So much boilerplate when you write C code, and yet it's the right thing. CBI dot parent j of I dot x equals x. I'll write this. I could have cut and pasted this from below as well. I spaced. Right, it's right here. Init grid. Oh no, not init grid. Oh, okay, so I didn't cut and paste that part. Oh wait, that's part of the good stuff. Okay, don't touch that, Sean. Right, so what happened to... Oh, build cluster. It's right here. So then we have to iterate over everything. And this time we have to range check properly. So let's go ahead and copy this code. And keeping in mind that we do only need to do double-sided, or not double-sided, you only need to do it in 2 directions. So we need to query the map. So we're going to need that, SBCC grid asterisk G, and then we need the X and the Y, rather than the cluster X. Oh, we have the cluster X and cluster Y. Right, so we can int X equals, this is J, I and J. Okay. So X is CX times SBCC cluster size. So you'll note, even though I know these are powers of 2, I don't use shifts for them. I don't use the log2 stuff. I only use the log2 stuff to avoid divides because I don't trust the compilers to take out divides. And the reason I don't trust compilers to take out divides is because the divide in C rounds towards 0 rather than rounding towards negative infinity, but the shift right of a signed number rounds to negative infinity. Therefore, the divide and the shift are not the same, and so if you specify a shift, it may not use a divide, or it'll use a divide and some fix-up code. But you don't need the fix-up code, you only need the shift. So I reflexively, as a habit, do this underscore log2 stuff, make everything powers of 2 so I can use shifts instead of divides. If you divide by a constant, it will turn that into a multiply by constant typically. But, and that could, be better for cache usage because you don't force things to be powers of 2 everywhere, but whatever. So then this becomes SBCC in cluster union. And this is kind of an interesting thing I do all the time without really thinking about it. I want to point that out. I don't know, maybe everyone does this, but maybe people don't do it. So like I know I'm changing onion to union, and rather than replace the whole thing and retype it all, I only typed up to the U, right, and then deleted the O. But then for the next line, which was also onion, right, rather than, my cursor is here, so rather than copy the whole thing and paste that over onion, I just also did the same. My cursor was already here, so I just did that and just replaced the O. So, I don't know. Maybe everyone does that. I don't know. That's just a thing I do nowadays all the time without thinking about it. I think about it a tiny bit, but okay, so now we need to actually range check. So what we'll do to make this efficient, which is perhaps overkill, is we'll split this into 2. So this loop is this, and this loop just, well, it's just the current value of j, right? The j outside of the loop will now be 1 higher, so it'll be at this value. So this is exactly the same thing. I've just split this out. But I know I can't test j plus 1, so I can just skip that one. And I know I can't test plus 1 if this was at the last spot, so I can skip that one. And so this one also goes, let's go ahead and split this like that. That's still the same, it just does them in a different order. But now we can skip this one. So there you go. I didn't add any range check. I didn't want to pay the range check on every if. I didn't want to have to range check every if. So this way I don't do any extra range checking. Now the map queries are still wrong. The map queries need to be, I didn't actually write a macro for this. So the macro is find SBCC map byte index for x and y is y shift left. It's the stride, the map stride. SBCC map stride. Oh, it's times that. And as I said, I'm willing to do the times because I know that will turn into the shift. And then plus, we take the x, and we shift right by 3. Map byte mask, which really only uses x, is going to be 1 shift x and 7. So people can double check that I'm doing this sanely. I love alt cursor selecting and inserting. What is alt cursor? It's like move by word or something. I probably have move by word in this. I just don't use it because I've never learned it. I don't. There is. What did I just type? I don't know. There is some kind of move by word, but I don't remember what it is. Never learned it. Don't use it enough. I said that twice now. Hurry me. Okay, so at that point we've found all the connections. So now we want to label them all. So, and actually maybe we can just propagate that out to the final data structure without labeling. Maybe I don't need the label data structure. So we iterate over all of them. Oh, and we need to probe for neighbors. We can do that in a separate pass. That's fine. Because we need to do it differently. That's not a very good quote. Oh God, now you're going to quit that. Damn it. Oh, multi-cursor. So what am I doing here? Oh, right, I'm finding who the parent is. So stbcc. Why does he say include? Did anybody catch that? In cluster. In cluster. Find. Like J. And that's going to return. Oh, I still haven't updated the map thing. Right. I just wrote the map macro and then I didn't use it. See, my mind just goes all over the place. So, what was the logic for this? Oh, he deleted it. Oh, right, if it points to itself. SBCC tiny point p. If p dot x equals I and p dot y equals j. Then it's the leader. Pretty sure that's a misquote also. Again, I could just be totally wrong. That I'm meaning to say one thing and saying a different thing, but pretty sure. Okay, right. So I'm trying to fix the map, and I just made the freaking macros. These. All right. So if grid map SBCC map byte index, it's so wordy, of, are those properly parenthesized? Yes, they are. Good. X plus I, Y plus J. What are we gonna, what's our convention? Is it, I believe it's 1 if it's open was the convention. Where did I build this? Didn't I build this somewhere? I thought I built this already. Did I delete that accidentally? Did I lose that in the crash? Init grid. Okay, there it is. Yeah, if it's open, I set it to 1. Of course, whether that's the right convention or not, you might do it the other way. Maybe we'll add a facility to pass it in already packed to bits so that you don't have to do this. All right. If it's where is that? Here. So that gets us the bit and SBCC map byte mask. Okay, so let's make a macro for this. Define SDBCC map open x, y. We need G as well. Grid. So that's grid, arrow, map, arrow. Let's just copy this instead of retyping it all. That's going to be really wordy and hard to read, so let's go ahead and do this. G, x, y. That is this part. And so then we say stb cc map byte grid x, y and byte mask x, y. And that returns non-zero if it's open. So okay, now we can say if stbcc map open grid x plus I, y plus j. I said I left that in here. I haven't saved it in a while there. Oh, you fix them in post. Okay, that's fine. I used to thinking of bots as being inviolate or something. Inviolate? I guess that's how you say that word. I guess I've never said it. So if that's open and the adjacent one is open, look how much clearer this code is now. Plus, this is the J case. Oops, I didn't delete all this crap. Yeah, see, this doesn't need to be all on the same line anymore because it's doesn't line up anyway, so there's no value to it. So this is now, this is, oops, y plus j, geez, x plus I plus 1, y plus j. And in this case, I'm actually going to do this to make it clear, because this is a little gross. Whoa, is that a bug in the original? No. Something happened when I tweaked it, when I was cut and pasting around, and I lost the +1 there. Okay, and then this one is just the same. It's this case. So actually, I could just go ahead and do this if j less than, instead of having the separate loop, -1. We do this case instead of having this separate loop here. All right. Of course, if we're going to call it rightmost column, I should call it bottommost. I guess they're different kinds of words. All right. Does that all make sense? I think that all makes sense. Then we'll move this back up to here. We already had that. Okay. Did I parenthesize G? Yeah, I did. Okay. Not that it would ever matter, but so. And SWCC map open g of x plus I, y plus j. Then we assign a label. Are we reserving the 0 label? Yes. No. No, we're reserving the max label. Okay. So this is cbi.label j of I equals label plus plus. Empty liters, and then we don't want to in-cluster find. We want to look at itself. P equals cbi dot parent of j of I. If it points to itself, it always is direct. It doesn't need to go through that indirection. Was that true in the original one? No, I directly checked leader. Okay. Oh, and here I directly checked leader. Oh, and then I did the find. Right, you could just always find. But okay, so then label all non-empty leaders. All right, and then I copied it out, and then label all other nodes. So now we do the in-cluster find. Or this is not equal j. So if it's not the leader and it's open, then it gets the label of the leader. And if it's closed, it gets the placeholder. CBCC next clumps for cluster, but let's give it a name. Null cluster ID. Cluster. Yeah, all this meta quoting, I'm not sure if that's really a good idea. Shit, you're gonna quote that. So what did I just call that? I've already forgotten. No cluster ID. All right. So that's basically cut and paste of the old algorithm. And so now within the cluster, we've run this. And when we do our init, we're going to have to do this in every cluster on every node. So the init case, when we first set it up, is going to be just as slow, and actually a little slower than the full case. But the goal here is to pay some extra overhead on the initial case in the hopes that the incremental updates can be fast. How much more do I think I have to do? That was not actually a question in chat. It's something I'm thinking about. So I was hoping I could do this pretty quick. It took me about 45 minutes to get the reference algorithm and some test data. And I don't know exactly how long into it was when it crashed. We're about 20 minutes, exactly 20 minutes into the new stream. I think the old stream was probably at an hour 15, hour and a half. So we're maybe pushing 2 hours. I think if it's not too buggy, maybe I have another hour. If it's too buggy, it'll take longer. But this is, we have to write this thing again one more time, and then we have some weird, crazy stuff to do. So, build cluster cluster. We don't care how this works anymore, so I'm going to move it out of line. Init grid is going to be our boundary line. Everything below init grid I'm not looking at anymore unless I start looking for bugs. And everything above init grid is where I'm developing actively. Okay, so we have to init the grid. We have to iterate over all the clusters. Oh, the width and the height. I wanted to handle these not being... Let's require these to be cluster multiples for now. Which cluster is an internal... No, it's not an internal thing. It's a explicit thing. So let's go ahead and assert that w mod cluster size x 0. That'll just simplify our lives for now. G arrow. So this is cluster, the horizontal, the width in clusters. WC? CW? I think CW. WC cluster size x log 2. Alright, I need to add those fields to the struct, so I'll just compile, and if I'm lucky, that's the first thing that will fail. Nope, it's not the first thing that fails. Oh, look at that. That's a pretty dumb definition. Yep, there we go. And now I can just warp up to here. That's my standard trick for getting to a struct. Okay. Cluster size is x log 2 because it's not double underscored because that's the parameter. All right, good. So we go to GCH. So we're iterating over all the clusters. Now we're going to say build clumps for cluster. Grid ij. Okay. So we've got that data structure now, but we don't have any info about the connections between adjacent clusters. So we need to add that. And that one is where we start to want to think about, and even this one maybe. So the idea here is that we're going to do this incrementally. So when you add a new connection, we don't actually process connections, we process nodes. Nodes are either open or closed. So when you change the status of a node, what we have to do is totally rebuild that cluster. We don't have to. We could try to incrementally rebuild that cluster, but it's got the same problem. If you deleted a connection, the number of clumps in there might totally change. If you did add a connection, we could try to actually incrementally do that, merge clumps, etc. But because a cluster is relatively small, we're just going to assume we always rebuild that cluster when you add a connection. So step one, rebuild the cluster. Let's document this. Void stbcc update grid. Now, eventually I want to actually add support to update multiple tiles at once, but for now, let's do this. Int y, int open. Okay, so g-arrow map of svcc map byte. What was this called? That's buried in macros. Map byte. So if open, and we want to set that map byte. Let's optimize the case where map byte and oops, right. It's not gr map. It's just sbcc map byte gxy and sbcc map mask xy. If that's true, it's already open. If it's false, then we want to set it. So we don't need to return anything. If it's closed, then we want the opposite. So we're going to mask it out, set it to 0. And we want to test if it's 0. So let's make those parallel. Okay. Once we get to here, we've now updated that thing. So what we want to do is rebuild the clump for that cluster. I should probably have conversion functions. Oh, I do have conversion functions. Cluster X for coord Y. For coord X. I do have that. SBCC cluster X for coord X. Okay. Any advantage for using degenerative triangles? There's no triangles in any of this. So, build clumps for clusters. So now I've rebuilt this clump, but I need to fix up all the connections adjacent to it. So, let's see. How do we do this? Find connections. Let's go ahead and have a CX. Let's see why. So I'm hoping, go ahead and ask questions if you don't understand this function. This function is like the core secret sauce of what's going on here. So we're updating the map. That's pretty trivial, right? The map is just a map of bits with the things. We're updating, we're looking at the cluster that thing is in. That's the only cluster that can change directly. So we're rebuilding all the clumps for that cluster. Next, we're going to have to find all the connections to adjacent clumps. Can the status of adjacent clumps change? No, that's the whole trick. If the adjacent clumps are connected through this node, doesn't matter. We keep them as separate clumps. That's the whole trick of how you can break connections because they get kept separately. So we're going to find the connections from CXCY in each direction. Oops. Right, we'll find, and what this is doing, what this will do is it'll run through all the clumps, it'll run through all the edges of our clumps and look for connections to adjacent nodes. So let's just go ahead and call that, to adjacent clusters. Let's just go ahead and name it that. Okay. Then we also need to find the connections back. Now, we have to think about this because each clump is storing, the question is how we're going to update that data structure. So in the adjacent cluster, we have a whole bunch of clumps. And each clump stores adjacent clumps. Now a bunch of those are now invalid, right? Because we rebuilt the clump. So the clump IDs, say we're rebuilding clump 3, 4. And it has connections to clump. So we're rebuilding, we just rebuilt cluster 3, 4. What changes in cluster 2, 4? Well, any clump in cluster 2, 4 that had a pointer into cluster 3, 4 is now invalid. So we need to fix those. And any clump that now has a connection into it needs to add it. So what we want to do, actually, before we update the map, we want to remove connections. Well, let me do this first. So then we'll find the connections to the adjacent cluster, and then so let's call this add, actually. Let's just assume it just adds them. It just assumes there aren't any and it adds them. And then the adjacent clusters, so -1, +1, -1, +1, need to go in the opposite direction and add the connections back. We're not going to, we'll do it single-sided. We're not going to, each of these is going to add them in a single direction, not add them in both directions. Cluster Y for coord Y. So I type in something somewhere. Where the hell was that? What function was that? It's just, the lag is so high. Oh, here. Yep, thank you. Right, so this will add all the connections out of this cluster to the adjacent clusters, and this will add all the connections from the adjacent clusters back in, which are just going to be exactly the same cluster. Like, it's totally redundant, but you'll see why the implementation of this means it might as well do them independently. I mean, maybe I'll change that. Maybe that won't turn out to be the right thing, but then here's the trick. Before we rebuild it, we're going to remove the connections from the adjacent clusters. And we are actually going to remove them from both, but since we're rebuilding it, we don't really need to remove them from the current one. But logically, what we're doing is we're breaking all the connections between this cluster and the adjacent cluster. And then re-adding them once we rebuild them, right? So does that logically make sense? And then at this point, we will say stbcc. What did we have the name? Build connected components for clumps. So I think that's the entirety of the update algorithm. So now we just have to fill out all these functions. This is going to be another find union disjoint set first. But now the clumps are not just a grid. They are actually a weird data structure. And then we need these functions. Void. Oops. Add connections to adjacent cluster. stbcc grid int cx int cy dx int dy. Maybe this, instead of being directions, should be no, because we actually need the directions for the relative cluster ID, relative clump ID, I mean. So let's go ahead and leave them as dx dy. I accidentally capitalize that. Let's go ahead and remove. Okay, so add connections. Let's look at what add connections is. So we're in cluster cxcy. We want to know all the connections to adjacent clumps. How do we do that? Well, it's pretty easy. We iterate around the outside edges, and we check them. And I'll have to add an extra data structure to make sure we don't add the same clump more than once. But the assumption is there are no connections to that cluster currently. The idea is that we'll have always removed all the connections first. So we'll have a list of connections to other clusters, but not to that cluster. right? Like we're updating the cluster that's to our right. So we can still have connections to the up and left and down. We're just adding the connections to the right. So we need to look at the top and the bottom. So int x0 equals 0, x1 equals with -1. So just for clarity, I'll go ahead and give these names. And we check if it's open. So if stbcc. Why did I use this and not stb map open? All right. J++. Thank you. The pair programming is super helpful. Somebody look at this and make sure that makes sense, because I kind of hacked that. I guess it doesn't work if W isn't a multiple of 8, but I think we'll live with that. So if the map is open in this cell, and what cell is this? It is G of Cx, so we need to int x equals Cx times SBCC cluster size X. I suppose I should have macros for this conversion too. Cluster size Y. I want to check Twitter real quick. I haven't checked that since I rebooted. All right. Sorry. I swapped out now because I was doing that. So what am? Oh, good. I left myself right in the middle, so I can do this. So this is x plus x0, y plus j. So if the map is open, okay. So first off, I'll just go ahead and do that. If cx is less than 0 or cx is greater than g arrow c width greater than equal to g arrow c width, or cy is less than 0, or cy is greater than equal g arrow c height, return. All right, so because I allowed this to just be called whether that existed or not. So we have to handle the case where that cluster doesn't exist. We also need to handle the case where the dx dy doesn't exist. Right, which we can just do like this. Okay, so, all right, and we only care, I was starting to iterate over every connection, every adjacent thing, but we don't need to iterate over every adjacent thing. We only need to iterate one side, because I'm doing these one side at a time instead of doing them all at once. So that was actually, it's not actually called cluster component, it's connected component. Connected components. Because maybe someday it won't just be grids. Maybe someday it'll be graphs and 3D things. So I'll just call it connected components now, even though it's only grids currently. So, right, so I want to do this a totally different way. So int step x, step y. Okay, so if dx equals 1, step x equals, okay, so how does this work? I, J, N, K. Okay, if it's to the right, then we're going to walk down from cluster size x minus 1. These should be double underscored. We're going to start on the right side. And we're going to step down. If dx equals, dx equals -1. Okay, nobody complained about my, nobody complained about this, so I'm going to assume it's bug-free. So we walk down the left side, step x equals 0, step y. Now this is a little inefficient in that, well, that should be an else. This is a little inefficient in that now this step isn't going to be constant, but whatever. dy equals -1. So this is upward. So we start in the same spot. Step x equals, like this would all actually be more symmetric if I rotated the starting point and always went clockwise or something. The code would actually be cleaner. But this is how I would loop naturally, so I'm just going to leave that. Else if dy equals 1. Let's just go ahead for sanity and, no, let's not. Let's do it like this. Assert abs dx plus abs dy equals 1. There we go. And then we'll go ahead and do this, even though it's not necessary. All right. So now we're walking across the bottom edge. So I is 0, j is g arrow. It's SVACC cluster size y minus 1. Step x equals 0. Step y equals 0. This is 1. And we have to have n, or count, equals SVACC cluster size y. Okay. At this point, we know how to walk. So we just walk for k equals 0, k less than n plus k. And we'll say I plus equals step x, j plus equals step y. All right. And then, if it's open, all right, now we need some way to know if we've already added it, but let's just assume we haven't added it yet. So SVC add connection to grid CXCY, add clump connection, grid CXCY. Let's do it. I'm going to do this super abstracted. Like I already have all the variables. I don't need to do this way, but I'm going to, this is x and y now. No, wait, it's not x and y, it's what, I and j. So I'm going to say that I've connected x plus I to x plus I plus dx, y plus j plus dy. Now, this is just going to recompute a lot of the stuff that I already have here, but just to make it clear, we can always switch and inline that. Okay, and that's it. I walked along the edges. If there were, if it was open in both places, right? So I need to check that the neighbor exists. I didn't do that. Cx plus dx less than 0, or Cx plus dx greater than or equal g w, or cy plus dy less than 0, or cy plus dy equal ch return. All right. And because we required the map to be multiples of clusters, we don't have to actually do any further checking in here. All right. So if both of them are open, that's the case. All right. Plus I plus dx. Oops. Then we want to record that there was a connection across between these two clumps. Okay, so add clump connection. What do we do? All right, looks like we're back. The fuse blew again. I've turned off all non-essential things, but I do have my lights on here. That's the first time it's ever blown out twice in the same day, so I don't know what's going on. It's very sad. Let's see if we lost anything. All right, what was I doing? Anybody know what I was doing at the time? I'm sure this is super frustrating for you guys, but trust me, it's way more frustrating than for me. It's actually, it's a, whatever you call a fuse that you don't have to replace the fuse. It's a, what do you call the, you know, that you just have to flip the switch. I don't remember the word for it. Remove connection, build connected components for clumps, add clump connections. So I was explaining add clump connections, I guess. Breaker, there you go. Yeah, it's just a breaker. Add clump connections. So had I typed any of this? I don't remember. So I was saying I'm going to have to recompute where these are in the clumps and stuff, even though I just had that info here. Just for the sake of this being clear, I can always optimize it later. I clearly need more booze, though. So, what I want to do is figure out which clump each of these is in. So we say SBCC, so we say int cx1 equals SBCC cluster x for coord x. Is that what this was called? Yeah, okay. I should have just cut and pasted that code up there. Yep. Right, remember I didn't like the idea of naming them CX1, CY1, etc. Let's just freaking do it instead of reusing them. Since I've written it now, no reason not to. Alright, so then we want to find out what the clump IDs are. So this is like the code to, what's the code to actually test if connected? Where's the test if connected code? What happened to grid nodes connected? Or should that have query? Should that be is grid nodes, are grid nodes connected? Test query grid node connection. How about that? I don't know. Size T rant link. Somebody, well, I guess it was on Twitter that the size T rant link happened. It was like 2:04 in the second to last OBBG stream, 2:02 maybe, 2 hours and 2 minutes, something like that. Oh, and I don't know how this is going to go in terms of uploading to YouTube now, because I probably have lost the OBS streams here. I may have to just upload the Twitch streams, which are kind of worse, and I'm more of a pain in my ass. All right, what was I doing? So the grid node connections. Oh, right, G clump for node. So it's this stuff. Right, which don't take cluster IDs. So C1, C2. Oh, I should just cut and paste. Yeah, jeez. Okay. So I know these two are in different clusters. And I know that CX1 minus CX2 plus add CY1 minus CY2, they better be adjacent clusters. So now I know which clump each of them are, and I want to add a connection for X1. Yeah. So this one, add connection to C2 in C1. So, STBCC relative clump ID, is that what it's called? Relative clump ID, yep, okay. rc.clump index equals C2, rc.cluster dx equals, I didn't pass that in, but it's just x2 minus x1, cluster dy equals y2 minus y1. Now we need to add that to this cluster. So cluster, so G arrow cluster C y1 C x1. So we want to add, no, we wanted to get a clump, not a cluster. Arrow clump C1. Okay, let's go ahead and actually compute that where we need it instead of in advance. So clump, this comment goes here. So that's the clump. So to the clump, we want to add an adjacent clump, and that is clump arrow num adjacent, and we're going to increment that because we're adding one to it like that. So we're just adding to that array. Let's assert clump arrow num adjacent less than, what's the max of that? Max exits per clump. So we don't overwrite the array. Yeah, I can, yeah. I already said. What's this refute link? Do I want to look at it? I think Sean McGrath also did a rant about size T, or somebody else. I saw another rant somewhere. Right, so we're just keeping an array. Now to delete it, we're going to actually have to search the array, which is a linear search, not efficient. But remember, we're just going to iterate over all of the exits, the adjacent clumps for a given clump. Normally, the number of adjacent clumps for a clump is going to be pretty small, like 4, right? 1 in each side for a big clump. If you do have a weird bumpy clump, you can have the weird max exits per clump case. But that's not going to be the common case, and we can afford the search. I think that's it, right? We added the thing. Should I be less obfuscatory? Should I do an int I do I equals, is that clear? I don't know. I have 2 variables named clump here. That's clearly wrong. Okay, right, RC. Right, so we've added the connection to the adjacent clump. Now we want to, now that's not actually done. But we're going to need the equivalent for remove. So let's go ahead and write that. It may actually want to work differently, but let's just go ahead and get it started. So at this point, what we want to do is find, so let's just go ahead and leave that, and then let's find that one. So for I equals 0, I less than clump, or num adjacent, plus I. If rc dot clump index equals, oh, we didn't do that, equals clump arrow adjacent of I dot clump index oops, y dx cluster dy. Now, yeah, like if this were C++, I could have written an operator equal to compare these. Of course, they're just a bit comparison of the whole struct, so I'd actually kind of just like to compare that as a 2-byte value. But how many places am I doing this? How much code would I save? If this is the only place where I do this comparison, then writing the extra code somewhere else to do this comparison isn't a big one. Now, obviously, flattening this out is possible. Whether the compiler is going to do this efficiently, who knows? Like if I do this inline and then break. Okay, so we found the match, so we want to delete it. So we say clump adjacent clumps of I equals the last clump adjacent clumps of clump num adjacent. The last one is one earlier, so it's that. And on this one, I'm not going to simplify out with the I. And if I'm not going to simplify out this one with the I shouldn't bother simplifying it out over here either. I should just make these symmetric. So if you don't like it in line, we can do it this way. If I is less than clump num adjacent, then delete it. Else, I'm going to assert that we should never call remove unless it exists, because I'm going to try to make the logic outside this do it correct, so we avoid searching these arrays extra times. 4 ++ I, not ++ j. Yeah, that's that compiler would have caught that because there's no j here, but might as well. Remove clump connections. Does that seem reasonable? Now, obviously, I don't need to store this in this RC, although it does allow that the potential 2-byte comparison. I guess I could union them up if I wanted to make that explicit. Right, so I think we just need remove connections now. Oh no, I need to fix this. So one of the problems here is that it's going to add the same connection multiple times. So what we need to do is flag if we've ever added a connection to a given adjacent clump. So what we need is, what are the max clumps per cluster? Is there a variable for that? Max clumps per cluster. So let's have that as a log2. So we can use bits. Oh, how big is that? It's like 1K, yeah, because I have to initialize it, so I don't want it to be too big. So that's just this. And then this becomes SDB CC max clumps per cluster. Okay, so we just want to flag whether we've already connected to a given adjacent cluster. So max clumps per cluster log2. Max clumps per cluster log2. And initialize that to 0. Oh, that's in the wrong function. It needs to be in this function. All right, so we need to find out what the adjacent clump ID is, which is this. Which is y plus j plus dy, x plus I plus dx. And remove for I 0 to j plus plus. Well, I already fixed the j plus plus, so I'm not even sure which loop it was anymore. Was it this one? I certainly don't want to remove the loop entirely. So this gives us the SDBCC clump ID. Am I using C already? Nope, but I have lots of variables named C. CX, CY connected. And then we want to say if we haven't already connected to that. So that is connected. Let's see, shift right 3 and 1 shift right CM7. I keep doing this bit manipulation. Maybe I should have that as a macro. Then mark that we have connected to that one and add the connection. So now we'll only connect to it once. We won't generate multiple connections to the adjacent cluster, which is important because, I mean, I guess the bounds doesn't change, but... Oh, remove what's the function name. Okay. Yeah, there's a bunch of, I get a bunch of corrections in chat, but because the Twitch chat is behind and I only look over every so often, some of the times I've already fixed it. But that's okay, because some of the times I haven't already fixed it. So good job, everybody. So remove, I need to do the same thing. If I've already removed the connection, I need to not remove it. And I think it can just be the exact same logic, except it's not called connected now, it's called disconnected. Okay, there. I just cut and pasted the whole thing and reversed the names, and I have no idea if that's correct. We have to call remove while the map is still open, so that we know we should remove it. So let's make sure we did that. Nope, we didn't. We actually update it here. Why did that? So we need to actually... We're going to have to test this twice. We have to actually do the update afterwards. So that and that. Right, because we want to do nothing if the map's already in the right state. If the map's going to change, remove the existing connections. Theoretically remove them from the current cluster as well. But we're just going to rebuild that cluster from scratch. Actually update the map. Rebuild the cluster. Add the connections, add the back connections, and rebuild the overall connected components. Really close. And then the initial state. But the initial state will just use all these functions. Cough line numbers. I assume you're saying I should turn on line numbers and then you would be able to tell me what the thing was. I don't know how to turn line numbers on in this. If anyone knows how to turn line numbers on, I'll turn them on. But I assume nobody else knows VC6, so... I'll check real quick. Is it options or customize? I don't see it. It's not going to be in tabs. Yeah, if it's possible, I don't know how to do it. Feel free to Google VC6 line numbers, but I doubt you'll find anything. Under tools options. Yeah, that's what I just looked at, but I didn't see. I mean, I didn't check everything, so. Maybe it's under tabs? Nope. Compatibility. Nope. All right. So, build connected components for clumps. Is that really all I have to do? Because that's just another one of these find union things. Okay, I guess that's it. Well, wait, so... Wait, no, wait. What was the function where I labeled all the nodes? It had the... Oh, right, I modularized it. I moved it to the end. Build clumps for cluster. So this did this thing and it labeled them all. But I didn't actually build clumps. So... And this is why I was saying I maybe don't need the label data structure. Because now... let's iterate over. The labels started at 0, so those are the clump IDs. So we just say, do we have the pointer to the current cluster? No. SDBCC cluster. Can we just call it C? Are we not using C? We're not using C. It's too bad the clusters and clumps start the same. I should have called it something else. We can rename it. Just do a global search and replace and rename it. Yeah, maybe instead of clumps, they should be chunks. No, wait, that also starts with C. So C is address. G of clusters. Whoops, I didn't autocomplete on that. CY, CX. C arrow. Let's see if that fixes it. Sometimes that fixes that. Nope. Okay, that probably means I have a compile error up here and it's breaking the parse. So let me go ahead and fix that. Max clumps per cluster. What did I end up calling it? Max clumps per cluster. SDBC max clumps per cluster. It's right here. Max clumps. I just got and pasted it. Must not be seeing something. Nope, it didn't change. Undeclared identifier. Oh, yeah. Forgot my ands. Tools, options, text editor. There's no options text editor. There's editor. I think you're looking at a later version than the version I have here. There's no text editor option. For type, void SDBCC grid. That is what it's called, right? SDBCC grid. Is this one not? Yeah, that one's not. Missing underscore. That's not correct. It's -3. In fact, this I could just use div8. Let's just use div8 instead of log2. Because this is compile time. So who cares about the rounding problem? It's not a performance issue. Map open, map byte. What else did map open take? GXY. It takes 3 parameters. Then it calls map byte, which takes 3 parameters. It calls mask, which takes 2. Map open. Oh. Map byte mask. Okay. Lost the underscore in that. Yes. Yeah, you can see the line number down here. Is that on, does that show up? No, it doesn't. You can see the line number the cursor's on here, but that won't help you when you see a bug that's not where the cursor is. And illegal. Left operator has type unsigned char 128. Okay, so map byte isn't defined correctly. Oh, because map is 2D. I forgot I did that. Because I made that all static. Let's give semicolon. Too many parentheses or missing parentheses? Oh, missing, yeah. Add clump connection undefined. What did I call it? Add clump connections. This should be singular. The caller was correct. I only add one connection here. Say missing comma because I cut and pasted this, which means this will also have a missing parenthesis. Oh, and the missing semicolon. Disconnected, undeclared identifier. I thought I changed it to disconnected. What did I? Oh, that's weird. Did I change the wrong? No? I don't know. Could have sworn I changed it already. What? Didn't I? What was it called? Map byte mask. Now we're past where it was a problem. So, parent, CBI parent. Oh, these didn't get renamed. STB, CC in cluster, find. And these are STB, CC tiny points. All right, so I need to pass in G or CBI? CBI. Right, and this is that one. All right, so now I think we're past where that error, where I was having the completion problem. Oh, maybe we're not. Where was it that I was having the completion problem? Oh, it was down here, yeah. So I do have to keep going a little further. In cluster union, forgot the build info. And cluster find. CY used without having been initialized, but not CX. Oh, CX as well. Yeah, we have to compute this at the beginning. Okay. So now what was the thing I was working on that wouldn't tab complete? Build clumps for cluster. Oh, right. So I was coming back in to do these labels, and I was like, C arrow. Hey, look. Why does C arrow? Oh, it's the cluster. Right, so I'm building clumps for the cluster. So C arrow num clumps equals label. C arrow clump of I adjacent clumps equals 0. And let's rename that label for clarity. So this is its label in the full grid. So we'll call it the global label. That's the actual connected component. Okay. So I'm 30 minutes into this one. I don't know. I've totally lost about when I started. Maybe I'll check the tweet and see when I started according to the tweet. Hours. Yeah, Twitter unfortunately rounds it off, so I can't tell exactly how long it's been. But all right, so we're probably at 2-ish hours on the library version. Where was I? Those ones for cluster. So we do in here, and that's all that, and we just need to do this. And do we have the X and Y? Yes, we do. So this is G arrow clump for node J of I, not J of I, X, Y plus J, X plus I equals CBI dot label J of I, which means we could just initialize this up here because it's not doing any good locally. And even possibly this one. This was why I was saying we didn't really need the labeled data structure. I suspect we could just get rid of it all. But we'll just do it like this for now. Okay, so it has really been 3 hours. So there's just this one function left to do, which is just the find union again. And the clumps need to refer to each other, and they can't use the relative IDs. So they actually need type of struct svcc global clump ID. So this is going to use unsigned. Well, let's just do this. Unsigned int clump index 12, unsigned int cluster x, and let's see, that gives us that many bits. So we're restricted to, why was clump index 12? Oh, because that's how much room I had. So, like, imagine if you had a really big map. 20 by 20, 2 to the 20 by 2 to the 20. Oh, you couldn't fit that in memory, so 2 to the 16 by 2 to the 16. You might want to bump up your cluster size, but you're limited to a cluster size of about 64 by 64 here. So then that gives you 64 times 1K, 64K. Okay, so yeah, that's about reasonable. And this is putting a hard limit on how big things can be, but 64K by 64K, yeah, it's probably a reasonable compromise. Tools, options, all languages. I don't see languages in here at all. Nope. Yeah, that's some newer version of Visual Studio. So this should be STBCC, so it doesn't conflict. So yeah, one of the things you can see here is when I make all these STB libraries nowadays, I just prefix everything up front. I don't try to go add it later. And it does lead to lots of extra typing while I'm doing it. And maybe I should instead, you know, search and replace clump ID with STBCC underscore clump ID, etc. But the search and replace, like, there's other clumps, like you could easily have errors with that. So it's just kind of easier to do it up front, even though it's more typing. I don't know. No, that's just how I've ended up doing it now. All right, so what was I doing? Oh, yeah, I needed to do this search. Why did I copy this? Oh, that was a... Wow, I'm getting lots of glitches now. VC6 does not normally glitch like this. Right. So let's freeze all these. Static. I don't actually even need that. Yeah, I don't need those. So these 4 functions: add clump, add connections, remove connections. I'm going to move down below update grid. Right, update grid is what I said was going to be the frozen spot. Actually, it should be a knit grid is the frozen thing. I should move a knit grid down there and make that be the root. So it should go right below update grid. Yep, okay. All right. What's build connected components for clumps? I don't even remember. Build connected. Didn't I implement this? Oh, right. No, this is the, yeah. So there's two things. There's build connected components for clumps. No, right. This is the global. Right, yeah. No, sorry, I just got totally confused. So now this is VCC point. Some short. Oh, this is still using that. Unsigned short XY. So we just want to replicate the find union sort of a little bit, kind of, but different. These are clusters, so they don't actually, that's actually not going to be, I'm not going to use point. That's actually wrong. Okay. So here's the code I need to copy. And the other code we won't copy because it wants to work differently. So we don't actually use point. We were going to return. What are we trying to do? We're trying to connect up clumps. So we're going to return the global clump ID, whatever that was called. Global clump ID. We're going to return the global clump ID, whatever that was called. Global clump ID. And takes a global clump ID. This is the more normal way this algorithm is described, just in terms of graphs. You just have nodes and you return nodes. So global clump ID. So the first thing we do is we need G. This is going to be a little inefficient in terms of indirections here. So we're going to say G arrow cluster node dot cluster y dot cluster x clump of and dot cluster clump index. Okay, here's a clump. So SVCC clump is that. So then we're going to look at C arrow parent, which is global label. Which is just a clump ID, a global clump ID. So for this, we do need to compare clump IDs. So let's go ahead and static int svcc compare clump ID svcc global clump ID A svcc global clump ID B. And of course, what we'd actually like to do is just compare them as bytes. So actually, let's go ahead and do that. Union. It's a union at the top level. It's either a struct, that, or an unsigned int. So this is fields, and this is code, let's say. So then where do we access this global clump ID? Probably nowhere yet, other than this function. So this is n.field. Okay, so then we want to know where the C arrow global label dot. Why is this not C arrow global label? What did we make the global label be? Oh, SVC global clump ID. There we go. So if the code for that equals the code passed in, If it points to itself, then we return itself. Otherwise, we run recursively, clump find. We don't need CBI anymore. That was just from the old thing. In fact, let's just start updating this here. I'd use memcomp instead of the union. But the memcomp could turn into an actual memcomp function call that doesn't get inlined when you're using an old compiler like VC6 that would actually do a byte-by-byte comparison or something terrible. So because of that, I'd use the union and just make it explicit. You're right, if you could rely on the compiler to do that, which you probably can most of the time, if you're not me. If you can rely on the compiler to do that, that probably is clear. I don't like it because it takes the addresses of the variables, so, you know, potentially prevents the compiler from treating them as registers. It shouldn't. It ought to be able to optimize that all that out, but I just don't trust it once I take the address, so I'm just kind of paranoid. So I do it using unions that sort of more guarantees that I know it can do it the right way. But it would be clearer. You wouldn't introduce these dumb .c's and .f's. And of course, if I could use anonymous unions, I wouldn't need to introduce the .f. But there are some compilers that don't like anonymous unions, so VC6 is fine with them, but there are some other compilers that don't like it, so I can't use them, so blah. All right, so then we have to clump find on C-arrow global label.c, and then we have to update it, C-arrow global label, not just on C-arrow global label, equals Q, and return Q. I think that's right. And then global clump ID, SKCC clump union, SKCC global clump ID, N. So these are much more complicated with this addressing map, but I think it's okay. So this will be M, M, and M. And first we say if m dot code equals n dot code. We'll just do a fast check if you actually passed in the same clump. You probably never should. Yeah, let's not bother with that. So if c arrow global label dot c equals d arrow global label dot c, return set c arrow global label dot c to n. It took me a little while to map that back through. D is n. We're setting it to d, but that's actually n. Yeah, that's not very clearly named. M and N and C and D. I should probably name them something more parallel. MC and MD. Is that going to be clear or not? I'm not sure. Wait, no, that doesn't make sense. MC and NC. That's what I meant. MC and NC. MC equals N. Maybe that's clear. Older compilers have functions that are guaranteed to be inlined, but in the other sense, there's force inline. Yeah, I know what you mean. That's an actual intrinsic. Memcopy is a special function that's not really a function, and that's just not true in VC6 necessarily. I mean, maybe it is even. I don't know. Okay, I think that's all correct. So what do we have to do? We have to iterate over all the clumps. So less than cluster count y. We actually need to VCC cluster equals edge cluster j of I, C arrow double clumps, SBC clump equals address cluster clump of K. All right. What comes after K? Can't use L. I'm using M and N up here, so I wouldn't really want to use M and N as integers. H, G, H, I. Let's go back to H. For H equals 0, H less than clump arrow num adjacent. And now we establish that there is a connection. And this will do it bidirectionally, so we can try to optimize that out as well. Only add connections from larger to smaller clumps or something like that. So now we need cc global clump ID m, m dot f dot clump index equals k, m dot f dot cluster x equals j cluster, oops, that's backwards too, cluster y equals j, and this is I, and these are all constant. For the entire cluster. No, for the entire clump, not for the entire cluster. Well, actually. But it's a bit field, so let's just go ahead and always update it. I was going to say you could update some of it in one way, but some in another, but let's not. And then n dot f dot clump index equals clump adjacent clumps of h dot clump index and dot f dot cluster x equals clump adjacent clumps h dot cluster dx plus I. So close, so very close. I'm sure this will all totally break and it'll be hard to debug, but very close. Okay, at that point we have the N and the F, so we can say SBCC global clump ID, nope, whoopsie, clump union grid M N. Boom. Now it's interesting, we're just packing these up and then unpacking them here. So we probably should just pack them, pass them in unclumped here, unpacked here. RSTUVW, those are kind of floats for me. Is that a Fortranism? I don't know. Okay, so we need to initialize all the clusters to point to themselves. All the clumps, I mean. So now we see cluster, arrow, clump, k dot global label equals m. Okay. And then go through all the clusters again, all the clumps again, and force them to point to the root. But we'll go ahead and just leave them as clump IDs. We don't have to convert them to colors. Or at least say, we just call STB clump find and discard the return value because that does path compression. Oh, I still need to pack it. Oh, excuse me. What was this for? Did I ever use that up here? I used it here. To access the adjacent clumps array. So I could actually flatten that down one and store the adjacent clumps array. Oh, and the loop. But here I don't need it. Okay, so now they're all flattened. So we knitted them all. We flattened them all. Okay. And what we'll do at some point is we'll do a performance when we do update grid. We'll add stuff to measure what the cost of each of these steps are once it's working. For all I know, this is going to be slower than the naive algorithm that doesn't update everything, because this has all sorts of extra levels of interaction, uses way more memory, right? Who knows, right? This is a gamble that doing it the smart way might be more efficient. I can tune the sizes to what's spare, but all right, well, I don't know. Oh, I need to finish the init. Yeah. Label 1 is not member. Oh, these got renamed. So this is now global label. Global label. These no longer have zeros as a reserved value. Has to be CC global clump ID. And so I didn't add that logic. So what did I make those? Build connection codes for clumps. No, I want build clumps for clusters. So what do I do here if it's blocked? I set it to null cluster ID, but that's no longer valid. This is we're going to compile anymore, I think. Oh no, this is. Yeah, this is not right. This clump for node needs to point to. This is not right. Clump for node. What type is clump for node? It's a relative. No, it's a clump ID. Oh, because it's within clump. Yeah. Right. Yeah. Okay, I just got totally confused. That was nonsense. Nothing I said there made any sense. Okay, so we were building connected components for clumps. We get to here. We've stored all of our clumps, now our global labels. We don't care about empty stuff. Empty stuff. These are C1 and C2. So if C1 is SVCC clump ID null, or C2 equals SVCC clump ID null, then you passed in stuff that was off the map. Otherwise, we do this, and we say .code. Clump ID null. What did I call it? Null cluster ID. It should be clump ID though. I think it's clusters. Is there clusters? I mean, clumps. It should be clump ID. Did I just change that backward while I was talking? Did I change it from cluster to clump? Where was it? Oh, it's in the query function. Here it is. No, that's that. Where's the query function? There it is. Clump ID. This was already correct. I reversed it. So yeah, I still have to do the init, but we're getting there. Very close, except for all the bugs. Clump union. What's the actual bug? Clump union. What? How's that an invalid identifier? Do I have a clump union? Is this not bracketed? That's bracketed. Syntax error semicolon. There's no semicolons here. Syntax error type. That does seem like this previous one is wrong. Semicolon, semicolon. That's bracketed correctly. What am I missing? Global clump ID. Oh, you can't be void and global clump ID. Union is void. Yeah. So let's just do that. Incompatible types. These don't take addresses. So just u32s. Rename that. Adjacent. Oh, it's num clumps or num adjacent rather. Oh wait, no, sorry, that was the wrong one. Adjacent clumps of I. Wait, what? What function am I in here? Build clumps for cluster. Num adjacent. We're clearing all the adjacency lists. So these are explicit adjacency lists, which most people don't ever use as arrays. Adjacency arrays. Oh, clump ID. Okay. I have to finish. So it all compiles. I need to finish init, and then we need to run it and watch it totally fail. Okay, so init builds clumps for cluster. Then it needs to build all the adjacencies for everything. Which is what? It's this code. I could modularize this, or turn it into a loop or whatever, but it's pretty freaking clear because the columns line up. So this becomes INJ. And then all I have to do is run this final what's the final step in the update? Where's the update function? This one. Is that it? Am I done? Really? That can't be it. No way. All right. So then we have SBCC grid equals malloc size of G. Init grid G map with height. And that actually labels it, so let's go ahead and just measure that. And then we have to build color from it. So we need I and J again. Let's make that a function. Let's like not be racist. With the height RNG, so right map SBCC grid G, our file name, where's the reference code? This, okay. Oh, I don't have a good way to find the initial colors without looking into the data structure. right, let's go ahead and expose that functionality, even though it doesn't really make sense. In SWCC query grid open. Return SWCC map open x and y does not equal 0. Let's flatten that down to 0, 1. You see query representative is leader. Let's use the leader term. Y. We only need this for one of them. And here are the ones. In fact, we just, there's nothing's being added, so let's just replace the one with nothing. And we get rid of the 2. All right. So then if label .f oh no, right, it's if c dot if label dot fields dot cluster x equals cx and label f dot cluster y equals cy and label dot c dot f dot pump index equals c. Return 1. So yeah, just return that. All right. So that doesn't, that's reflecting the internals, and I could just do it in place, but whatever. So we say if SWCC query is leader, Gij, and then if SWCC query map open is open, what is it called? I forgot. Query grid open. Yeah, well, it's totally random. Wrong names. These all need to get fixed. Grid open Gij, and this. And then if bang STBCC query is leader, Gij, oh, then we need to know who the leader is. I really want to find a way to do this that doesn't reflect the internals, but I don't know how to do it. You want to find the first node that's not connected to, I don't know. It's so close. It's so close. I just need to write it out. I could just run it and see if it crashes, but let's just reach inside the data structure. Well, no, because it's a whole bunch of functions. Let's get rid of this, by the way. Right, so it's this. Leader. Oops. Oh, we don't even store a, there is no object to refer to. Let's return that. In fact, let me look up what that rand LCG multiplies by. It's not necessarily the best one, but it's something. And then we just have to use the same thing here. Which means we don't actually have to query if it's leader. Just this. Much simpler. All right. Is that it? Color SQI-G arrow W. All right. Let's find the compiler errors. Signed, unsigned. Oh, fart. What's the actual error here? See. Oh, it's that. All right. Don't even know if it's going to run. Stack overflow. Okay, so one of these is wrong. Oh, but we made it to the clump find. We made it to this step. That's interesting. Okay, so it's 1K by 1K, but we shouldn't. So the other one, the reference one, could have a bad case where it like uses 1,000,000 items of stack or something. Or maybe not. I don't know what the actual worst case is, but this one should only ever be able to do that. So there's an actual logic error here. Made it pretty far. I guess I should look at the stack. So n clump index 0, cluster 2, 2. And then let's go further up the stack. Hey, look, it's the same one. Hey, look. Oh, it's different. Aha, it's alternating between these two. So it managed to get a circular thing. So it managed to point something to itself. So M, 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 N, N, N. Check the initial values. They're all unique. J, I. Let's make sure they don't get truncated. All right, they all look unique. K, I, J. And then we do unions. It can't matter. As long as they're in range, as long as nothing's out of range. So let's run to there. Let's see what happens. Okay, we claim that we're at 0, cluster X, cluster Y is 0, clump index 0, and we're connecting to a different cluster's clump 0. So what do? We redecode that to find the clumps, giving us MC and NC. MC global label dot f points to itself. NC global label dot f (0, 1, 0) points to itself. Okay. So now we make... Well, these need to be a find. Yeah. Did I do that wrong in the others, or did I do it wrong when I copied it? That's a find. And then tiny point. Union. Oh, that's the wrong one. Tiny point. There we go. And that's a find. Okay, so I left out the find on this one. Right, because I had to do all this work to decode it, and so then I got kind of caught up. So then we do... Can't use L. M... Find. Got pass in G as well. I'll do that for N. And then we want to compare these. MP.C and NP.C. That's just MC.C. No. No. We have to reach back into MC. No. We have to reach into MP. Yeah, we have to reach into MP. So that's gr cluster of mp.f.cluster_y, mp.f.cluster_x, .clump, mp.f.clump index, dot global label. What is it called? Global clump ID. All right. Signed, unsigned, jerks. No, actually, let's do it the other way, so that we don't change JK at all. Although they should always be positive. Should be impossible for them to be negative. All right, let's try running it again. Okay, took longer. That's fine. He said it would take longer. C:\x cc. Did it not write it out? What did I call it? SUBCC. And it looks like it worked. Okay, so now we got to do the incremental stuff. So let's switch over the input to that one. Okay, that is weird. Are those the same color, or are those slightly different colors? I hope those are slightly different colors. They might be slightly different colors. Oh, that's too big. Was there an easy way I can test this? No. Okay, let's just directly encode that. I guess that's a little too weird. We'll do it like that. Now they'll all be partly transparent. Yeah, so this will be tricky. But let's see. How does this work? The top 8 bits are what? I don't know which order the bits get packed, actually. But our cluster IDs are actually currently pretty bound. But I don't know which way they get packed, so I can't really do that. Yeah, okay, so let's do this. Oh, I don't actually return the... Okay, let's do this. All right, they're all different. Okay, good. All right, so now what I want to do is incrementally update those gray ones. So we will int updates I can just do them in order. I guess I don't need to build I was going to build a list and randomize them, but we can just do them in order. For j equals 0, j less than height. For I equals 0, I less than width. If map of j times w plus I greater than 64 and map of j times w plus I less than 192. Now let's just actually do that. I guess I don't know what value the gray was. Then we say STVCC update map, update grid ij, and we will open it. And we will write out, and this will be slow because writing is slow. We'll write it out every row. If there were any changes. Right, J. That's 4 digits. I don't want to write 4,000 out. Oh, but there won't be. Right. It's only the rows that have changes. And then we won't close them again, which will disconnect it. The very first row will disconnect. The very first row that has any changes will disconnect. So that's close. And again, I haven't tested this path yet, so it could crash. And I should write this out to a different directory. So I can look in the directory more easily. All right. So now it should init in the same amount of time it used to. Oh, I don't print it. Let's fix that. Yeah, I need to modularize this into a function so I can run it multiple times. Okay, good. All right. So now we go into x stbcc row. Those aren't actually connected. Oh, there they connected. Are they just similar colored but not the same color? Gosh, that's so hard to tell. I really need to recolor them clearly. But you can see they do change colors once they connect, so I think that's a good sign. Now, are they connected to the other side? They are. Now here... Oh, because it... Yeah. Okay. So it opens, connects on both sides. Connects. Okay, but that's the easy path. So now it's the disconnect. Boom. Wait. Oh, that was a different file. Okay. That's the very first disconnect step. That one disconnects. That one disconnects. Woo! All right. Seems to work. That's kind of surprising. I mean, I did have to fix a couple bugs, but they were bugs that just crashed or whatever. You know, they weren't bugs I had to do a lot of debugging to figure out. There was just that one, the stack thing, right? Did I have to fix something else? Probably did, and I've forgotten already. So now we want to get timings. So let's do... Let's actually take it here. Oh, right, we can just save it. We don't need to return it. Because we're not going to nest these ever. It does prevent us from nesting them, but whatever. It's just quick and dirty. Dun, 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 dun. Double TM. Oops. Darn it. There we go. %s. Now let's actually put it afterwards so that they line up. Do I have to force it or does it auto space? I forget now. Used to know this all the time. Start timer, end timer. This takes void. We can get rid of all these. Oh, and that was debugged. Okay, wait. Start timer. I haven't actually checked the performance in release. Start timer, init. End timer. Start timer. Open. Let's do screen enough. Open. Return anything anymore. But use those. Look at those. Look at them go. Fractions of a millisecond. Now there should be one slow one. No, there shouldn't be slow ones, right? Because it always does the same work regardless. It always does the full rebuild every time. So it doesn't pay a cost when there's a big update. When it breaks apart, because it's still always rebuilding the top level thing. It's amazing that it's that fast. I did not expect it to exceed it by that much, especially because this is the bad cache usage one. Let's see how much memory it uses, so I can tell Nick that. And let's do it in release. Jesus. Let's check to make sure it still worked correctly. I think so. No, I haven't tested this very thoroughly. I have some other files I should be testing. But for now, we'll assume it's correct. And I'll give Nick that info, and then we'll move on to doing more thorough testing. What time did I start? How long have I been doing this? But it's looking good. Why was that STB sprintf not printing correctly? STB sprintf, which updates a static, and then it passes that into start timer, which copies it, but I don't do any other STB sprintfs. So it ought to work. Oh, I forgot to actually print it here. Okay. So release build. Oh, right. I have to Sean purge. So the actual reason I did this is because Nicholas Vining is a friend of mine who's working on Clockwork Empires, which is a sort of dwarf fortress-like. And he was having trouble with this subsystem that they have. And this was a system that I had thought about writing. I had written a version of this for 3D, but never finished it. 3D, it's much harder. You have to use sparse data structures. And he was having performance issues with it. And I've never seen anyone do this incremental version. I don't think it's, I'm sure someone has done it before. This whole idea of splitting into chunks has been done for pathfinding for like A star. There's hierarchical A star or something. It's called something like that. So the idea is pretty obvious. Let's quick. And the reason it's this much slower than this, that's not just scrolling by, is because it's writing out those files. Writing the files is what's taking the time. Because the PNG, you have to run a zlib compressor. So if I take out the file writing, it'll go by much faster. It'll be limited by the printing speed probably. Yeah, so. So yeah, let me tweet this at Nick. Because then he can just use this library and not worry about fixing his problems. Although if he's trying to get a release out today, he may not be able to wait for that. I did see a 1.02 millisecond one. It was when it shouldn't matter. It's possible there was a spike. Something else was running on the machine. It may not be consistent. Yeah, I don't see it this time. I don't see a 1. Yeah. Looks like worst case is 0.48. Not sure that's going to be consistent though. 515.488. 488. 515.488. No, now it's fast again. So yeah, these are being, I need to sort of, yeah, who knows? Who knows what exactly is going on here? Or it could have been the other one, right? 488, 515.48. No, that one was also fast. So big success here. Super fast. Has anybody had any comments about this? Nothing addressed to me. So let's go ahead and go ahead and put this into an STB-lib. Although I'd still have to debug it fully. Let me do this. My backup app, in case it prints out anything secret. I don't think it will. Oh yeah, there is the one secret thing. Haha. A project I have not mentioned publicly. Quick overview for us late viewers. Watch the first stream. You have a map. You want to do pathfinding on the map, but the user can customize it, like place buildings or something like that, like or do a fortress digging. And so areas can be disconnected from each other. And you can ask, you could give a command saying, you know, go from here, go from where you are to this other place. And if it can't actually reach between those two places, most pathfinding algorithms will explore the whole map because it doesn't know that there isn't a gap in a wall way up at the top corner, and so it has to search the whole thing trying to find. So it's not actually doing pathfinding. It's just to solve this problem that the pathfinder will explore the whole map, even though so like normally you only do short path finds, but the short path find is across a wall and it doesn't know how far, and you could like limit how far you path find, but this is kind of simpler. So the thing that you do is you just keep a reachability graph, which is just a connected components thing. So you just break your map down into oh, I don't have the old Einstein one. You color each disconnected area separately, and then when you want to pathfind from here to here, you check what color they are, and if they're different colors, you know you can't reach them. That's sort of the idea. Doing this in itself is pretty straightforward. The problem is that you need to do it incrementally. You keep somebody's building or placing things, and this connection becomes connected or disconnected. And most people solve this problem by just resolving the connectivity for the whole map every so often, because it turns out that doing that incrementally is hard. So this is a system that attempts to do that incrementally, but it only works on grids. It uses the grid structure to optimize it. We don't really need to add it to the project, but whatever. How big is this going to turn out to be? Anybody have any guesses how many lines of code that is? Okay. Yeah. Of course, people can type it into the chat and not know, it won't be obvious from the chat whether they did it before or after I did this, but. Well, let's find out now. And I'll never be able to tell whether they did it or not. 581 lines of code at the moment. Did I lose anything? Nope, I didn't. So it's not that big. 600 lines of code. I mean, I haven't debugged it fully, right? It worked. So I'm going to guess 600, but I don't know if they did it before or after. The other people in the chat know if they did it before or after. Oh, I should have typed something on this. Oh, right. Here, I'm about to paste it. Boom. There. Okay. Yep. Well done. Oh, I see. I had a different amount of lag than you because you obviously already verified it. Anyway, hooray. Good job. You win something. Okay, so that's the beginning. Now we have to say SVC connected components implementation. Put it at the top. And then we'll add the if-defs. No, if-def, yeah. if has to be, how do I normally do these? Has to be image. Don't I do an if-def? No, I don't on this one. That's dumb. There we go. Include. Yeah, okay. So I just do include. And if this conflicts with somebody things, well, we'll fix it. Connected components H. Because really, I don't know why you would use this symbol if you weren't this library, but hey, you never know. And if. Okay. So then we have to expose the grid to you so you know how big it is. There. Let's not expose the grid to you. So let's do std_cc grid type def. And then we'll have extern, and I need to change these so that it can be static. Size t std_cc grid size of. And that's a void function. And the implementation is going to be that way we don't have to expose it to you, but you can malloc it. You can't define it on the stack, but you should never define it on the stack because it's freaking huge. And it does mean you can't define it as a global, but I think that's not a big loss. So now here we actually do have it, so I have to be careful about this. I have to actually just make sure I do this. std_cc grid size of. Let's see what anyone said. Nobody said anything. All right, we're almost done. I'll have to add real documentation. I have to debug still, but we're almost done this refactor. So now we just have to move up the public functions. Let's rename query leader to get unique ID. And I ended up not needing query as leader, which is good because that was exposing internals. So grid open is redundant in that you might be keeping it yourself. You typically would be keeping it yourself in your own data structure and don't need to know, but let's check. Is that it? I think that's it. Do these use anything else? Nope, they don't. Obviously, documentation is needed. How do I do these normally? Like that. Let's go ahead and copy in the license so I don't forget. Where is the license? So at the bottom. Does this one not have it? Oh, I'm looking at an old version. Ah. SV image.h. There we go. Get that in there right away. So SV connected components version, let's call it 9.0. Public domain connected components on grids. This is stale. That shouldn't even... Oh, no, it's not stale. Right. I'm leaving that as the permalink for most of them. But github.com, nothing. This has to be. Okay. Traverseable, I think. This is all quick and dirty because I want to send it to Nick. I don't know if he's even going to use it right away or use it at all, but so let's name this traversable. Let's change this to 1. It's kind of backwards, isn't it? Should it be... Do you think the map should be 0 for traversable and non-zero is solid? That seems more sane. Check my Twitter. So I'm not necessarily going to do the full testing and fixing on stream. I'm kind of a little tired of this. Not tired, but a little tired of this. So I might stop without that. But I might. I don't know. And of course, I didn't even tune this cluster size. We could try tuning it. We'll do that as soon as I... It is traverse able. Okay. Oh, yeah. Okay. Oh, I didn't... Where's the query function? Here it is. I never tested this. I should probably test that. The main, what would you call that? Boy, I didn't drink fast enough at all. Literally never felt that. Primary, the thing you do all the time. What is a word for that? Initialization. Let's actually call these bonus functions just to be more explicit. Initialization. There's some word I can't think of. There's some specific word that I'm thinking of, but I can't think of the actual word. Primary. Yes, you would have to keep 2 grids for that. Or, you know, if you have large and small objects, you have to actually create some kind of virtual grid. Like, this doesn't have that notion of, like, oh, I need a 2 wide connection. So you have to actually build a sort of virtual grid representing that and track it all separately. And this uses a lot of memory, but, so what did this turn out to be? Clump for node. This turned out to be 2, right? And I did say I could cut this in half if I needed. And then this one turned out, though, to be big. Max clumps per cluster. Yeah, it's just one smaller than the full map. So that's 1K times 1K times 0.5. This should probably be times instead of by. Yeah, I guess. Whatever. Times times however big SCBCC clump is, which is max exits per clump. Jeez, this is huge. This seems like this is way bigger than I was thinking it was. What's max clumps per cluster again? Oh, right. I've already factored that into the 1K by 1K. Right. That includes the max clumps per cluster. So I'm not going to count this one in it, just as a simplification. Might as well align it. And then we're going to ignore these two and just count this. So relative clump ID, did that turn out to be, 2 bytes? So max exits per clump. What did max exits per clump end up being? Max exits, per clump. Right, size plus size, which is 32, 32, 64. Right, I've written it up there. So this is times 64 times 2. That equals, this is 10 plus 10 minus 1 is 19 plus 6. Well, these two cancel. So 10 plus 10 plus 6, 26. 2 to the 26, which is 64 megabytes. Oh, my circuit breaker went again. They are still doing stuff outside. 6, so they should probably stop pretty soon. I need to get my Twitch open. I can't see the chat at the moment, so give me a sec. Okay, it is working. So I have no idea where I was. I was trying to rename this. I guess that was where I was. Primary, update, the main thing, do it. There was some word that I totally now don't even remember that I had a word really, but main functionality. That's not at all what I want, but we'll call it that. And then the question is, does it still compile? Why is this changed? God only knows. Why is this different now that I've remodularized it? I have no idea. Have I disabled that warning somewhere in that code and now I've moved it before it? Oh, right. I need to rename this to get unique ID. Yeah, I saw the juicy bits originally. Okay, that didn't run. I didn't see why it didn't run. Oh, because I turned off the map writing, so it did run. It just was really fast. Yep, okay. All right, so now I need to check my Twitter replies. All right. So, I think that's working. So I should test the other files. What was the other one called? Oh, there's just map03. Wait, why are these? Oh, that's right. Right, there we go. 03. Now this one had no grays, so it's just gonna. Oh right, I changed the documentation, but I didn't change the code to actually match the documentation. So let's do that actually first. Right, so the meaning of the map. So it's solid. So let's do the update grid first because that's smaller. Int solid. Bank solid. Bank solid. That should be it. My memory tells me those were the only instances in here. Yep, okay, looks good. And then init grid. We need to change this to it's traversable. So we're going to store 1 if it's traversable. So that's 0. I think that should be it. And then, oops, typo. Then I have to change the caller, this test app, to actually do that. So we have to we just have to invert it, I guess. I think that does everything I need. I have to put it back to mapper 2 to test it. We need to actually make it write it out. is that? Why am I typing not typing? Hello? That's something weird that's been happening to me a lot. Why is the keyboard not stepping here? Why is it ignoring the keyboard? Or are they actually outputting all the same? Oh, they are all the same, so I broke it. Oh no, it was just too subtle. No, it's writing out stuff that didn't change. I'm confused. What is it write? Why is it writing some out here? Nothing's changing. Oh, because the closed aren't changing. That's opening, and the closing isn't working anymore. Oh, because I have reversed the meaning of these. There we go. There we go. Yeah, okay, that's how it's supposed to be. It opens them, then it starts to close them. Okay, there, it's finished. Oh, this is opening, base, close. Okay, that looks correct. So now, let's move back to, let's go ahead and see mirror. I need to be in this directory. I don't know if you can hear the construction there or not. The backing up. All right. So, right, switch map. Okay, so this is what I wanted to do if for map of 3. Such an old habit. Okay, it's apparently all connected. So, except for that. So what I wanted to do, and I don't know how well it'll work, is just start randomly disconnecting stuff. So for that we do for let's go ahead and use I. What is it called? Update grid G X Y solid. If I mod 100 0. Oops, that's got spaces in it. That's not good. How do you do that without spaces? Wow, I haven't... Minus? No, that forces a... Maybe it is minus. Is it minus? Nope, it ain't minus. What is it to not have leading spaces? Yeah, I wanted to stream an STB library from scratch at some point. And I mainly started OBBG just because I didn't have any STB libraries coming, so I wanted to start some project and stream it. But here we hit a good one. It was something I thought I knew how to do. The friend needed it. I suppose I could charge him for it, but really, why bother? Come on, what is the code for this? Looking it up is going to take so freaking long. Printf format string or format specifiers is probably better, but oh, maybe Wikipedia has a useful info on it. That seems kind of dumb. The minimum number. Left align the output of this placeholder. That's what I did. I did a minus, and it didn't work. Did I do the minus in the wrong place? I swear I did a minus, didn't I? Did I do it in the wrong one? Oh, do I have to do it? Did I do it between the 4 and the D instead of the minus? There's how you do it. Jesus. That made no sense. Okay. And it does want a PNG on the end. All right, here we go. Now we finally get to see if it works. Let's just slow. I don't see any. Oh, it's only doing one little tiny. No, it's doing 100 pixels. Oh, I'm not updating them. I'm not actually updating the map itself. Yeah, because we look at map here. Over here. Where do we write the... Oh no, we just query... We do query open. We don't look at map. Am I opening it the wrong... Updating it the wrong way? This connected it, this disconnected it. So this should be disconnecting. Let's do more. I think it's just not working though. I think I'm doing something wrong. It's super fast, so I can do as many as I want there. Don't know if this is the new batch or the old batch. 621 is the new batch. Oh, I see. Yeah. Delete. Open random question01.png. I'm a little suspicious about 1301. Oh no, okay, that is right. No, nothing. Oh, change color. Oh, there's lots of little tiny dots. Oh, right, because this is scaled up. Yeah. Yeah. Okay. So what we need to do is draw a big blob, which is where the batch updates would come in handy, but whatever. We don't need them. That's fast enough. So the point of the batch updates is you would still recompute every cluster immediately, but you wouldn't bother recomputing the full connectivity. Oh yeah, and I said I wanted to time that. Okay, wait, let's, first of all, let's delete all these so we know the fresh ones. It's taking its time. There should be a little blob somewhere that it erased. I think that's it there, maybe? Maybe not. Okay. There we go. So eventually these will randomly happen to cause a disconnection somewhere. There we go. There's one. I don't, my slideshow thing doesn't ever rescan the directory, so it's just however many there were when it started. Okay, let's actually do this. If has to be rand and 1. Let's draw. Doesn't correctly update. I want to be able to tell, so I need to little horizontal and vertical lines because we want to, if it actually have visible enough breaks that I can tell whether it's actually working correctly or not. So there should be a horizontal or vertical line somewhere. Yep, right there. Okay. Okay, right, so that produced 2 little things there. That split that, but it's still connected by the various paths. Is that actually disconnected? Yep, just barely. That got disconnected. Where did that get disconnected? Down at the, down here is what changed. All those other breaks were already there. And then this one. Yeah, yeah, that all makes sense. Okay. I don't remember if this goes in numeric order or not. I think it does. I think I did add the logic. Yeah, it does. Okay. Rather than the string compare order. So that looks like it's working. I mean, I'm not super verifying that there aren't other things, but like right there, there's a 1 pixel gap. It looks pretty reasonable to me. I think it's working. So, you know, maybe we should do some kind of more thorough testing, but I don't know what would be a good unit testy kind of test for it. I don't know. Like, I guess make a maze that's only got one way through, a labyrinth, and cut it in various places and check that no matter where I cut it. There's all that boundary stuff for having the really fine-grained stuff, so I can make a really fine-grained labyrinth. Anybody have a good pointer to a maze generator? I can generate a maze in my sleep. You can use the union find to generate a maze, actually. That's kind of awesome. Maybe I use the reference version here to do it. Okay, well, let's go back to the library side and see if there's anything more I can do before the initial release other than check for more bugs. Oh, performance. I wanted to test the performance. Yes, yes, yes. So what we wanted to do is test where within these things, within these steps. So what's yeah, I need to reorder it. That's one thing I need to do because I'd move things around. And I could do all the optimized things. It's already so fast, I don't know if I want to, though. Oh, I have to test this. Right, right. I haven't actually tested the primary function. Okay, let's do that. Is there a good way I can do this? Is there a good way I can do this without having to have an interactive thing? That's the question. So I think what I'll do... I'll just hard code it based on one of the maps. Oh, I should do the random test on. So if I just pick halfway and a little bit down, hopefully that'll be inside. I mean, I am doing the coloring stuff implies it should be correct. It's just I might have a typo in the thing. So 512 60 to 512 10.4 minus 60. So right before we print the timer, we'll test connected. Test connected takes G. If one did, oh, I didn't switch maps. Oh, and I could try the Einstein map again too. Hey, look, it crashed. Woohoo! C2 looks pretty invalid. Y2, X2. Why is that one invalid? That looks uninitialized, right? Yeah. It's Y2, X2 out of range? Is nope. Y2, X2. That seems right. Yeah, I'll do the Einstein after I fix this. Assuming I don't freaking power fuse box circuit breaker. There you go. Assuming I don't have the circuit breaker trip again. Circuit breaker trip again. Circuit breaker trip again. Yeah, that is a little bit of a tongue twister. What am I missing here? Like, all the other logic works, because the coloring works, so there's nothing wrong with this stuff. It's just I'm missing something. But C2 just looks bad. But I do use C2, right? When I get unique ID, I get clump for node, y of x, y of x. The x and y are not out of range. When I do the coloring, I would query that one. Width, height, queer grid open. Only if the grid is not open. Maybe it's uninitialized if the grid is closed. Maybe I missed that. I meant to do it, and maybe I never did. What is the null clump ID? Null clump ID. It's the max clumps per cluster, which is one shift left that, which is this minus one. Max clumps per cluster, cluster size. Look, dude, so it's 10, 9, it's one shift left 9. Should be 512. Okay, so then the question is, are we actually filling that out? That would be in build clumps for cluster. Why don't I search for that instead of looking for it? If map is not open, we set label to null clump ID, and then we set clump for node node size. Right. I mean, they're the same anyway, but y plus j, x plus I, ji. Sure seems like it should. Insert gr clump for node y plus j, x plus I is less than or equal to svcc null clump ID. And let's do that after the init as well. Hello? What is up with this keyboard just stopping working for a while? There it goes. It's so weird. Some Windows problem or something. So then I want what? When I init the grid, let's do that. So let's try that. See if any of those asserts fire. This needs to be I and J. Assert fired. This did not work. Yes, this is incorrect. Because they point to themselves. So we need to do it this way. Why is this now failing? Did I break something in this function? Yes, I lost some curly braces. Okay, it's disconnected. It may stay disconnected the whole way because I may not have picked the right coordinate. I'll go into Photoshop. Where's Photoshop? Oh, I see a 0. Oh no, that was a 1. That was a time. File, recent, map to, coordinate, 5 or 270. What was it? I said 51260. 51260. That looks good. And then 512. Ooh, 512 is over here. 512,871. Or what's that? Where did I do that? Oh, oh, I never called it. No, I do call it. Yeah, I do call it. Okay. 871. Yeah, that was too high. Too low, rather. Let's move this down a little bit just to be on the safe side. All right, there we go. All right, so it'll still start off not connected, but should connect up at some point. There it goes. Only for 2 rows, though. Is that right? Was it only 2 rows of the... I guess that makes sense. Should only be the last 2 rows that they turn the same. Yeah. Because, once it connects, it is about to stop anyway. It has barely any gray to fill in. Yeah, there's only 2 times. All right, so I've tested one case and assumed that it's working just from testing one case, which could be wrong, but we'll assume it. All right, so let's do Einstein. That's 1. And turn back on the random mode. And delete, start a PNG. And I don't even need to switch to release. Seems a little slower. I mean, yeah, this yellow region here seems to work. It's hard to disconnect these big regions. It doesn't really tend to, it tends to create little local disconnected regions, but it doesn't tend to split them in half. Only when they have this weak connection like this do they tend to split in half. Like I'm expecting some large chunk of this to go, but it hasn't. That changed color, but it's just because of something else. Now this middle region split it again. Here's a little region splitting off that. Yeah, I think it's working. Oops, open random. Yeah, there's that finally getting split up. There's a split on that. Let's see what that split is. Oh no, it's already split. No, okay, I see it's connected through that. Yep, and then the perk goes ahead and splits that. It has other uses as well, but that was the motivation, the primary motivation. Okay, I think that's working. Right, so performance. I wanted to test performance. So let's not use the random one because that updates things that aren't actually changing. So let's switch back to mapper 2. Although mapper 2 is so sparse, let's actually stick with this. Okay, so you need start timer and end timer. We're just going to use this from inside the lib in a hacky way. So we go in. Start timer, build clumps cluster. Init. Join. Oops, I forgot my closing quote. Got my end timer. I guess I could have start timer automatically end timer. Timer. Label. We won't even bother timing this stuff. Actually, that's part of labeling, so let's go ahead and do that. Because we won't know if we should optimize this, so let's time it all. And then so I'll get run as part of a init, even though I didn't actually want it. Okay, then this was the other place I need to do. So we say start timer here. Update grid remove. Timer. Build clump has its own timing. Timer update grid add. End timer. And then build connected components. Do I want to have a broken down thing? Sure. Start timer. Build connected components. Init. Remind me if I missed an end timer corresponding to a start timer. Let's cover the whole thing. I forgot the including quote again. Wow, what a pattern. This is join. End timer. Start timer. And of course I use start and end, which is not symmetric. And this is label. End timer. Start timer, end timer, start timer, end timer, start timer, end timer, start timer, end timer, start timer, end timer. Okay, good. And then I have to get rid of the start timer, end timers in this. Not that. Oh yeah, that one. And these. Oh, this is inside the F0, so not these. These. Oh, these weren't having timers. Okay. Printf undefined, of course. Yeah. Not in VC6. C only. Can't do either of those things. Okay, good. So now, update grid. Oh no, it will show update grid remove. Okay, that'll be the start of an update grid always. Okay, so let's do release. Quick release quick rather. Okay, so I'm stuck in build cluster cluster here. Is that because this is all the init? How many times should it do this? I guess it has to do this 1,000 times in init. That seemed like a lot though. Okay, so here we're in the middle of some updates, so let's go ahead and break it and see what it looked like. Update grade add. Build connected components. Wait, so what happened to update grid init? Oh, it starts with a remove. Remove, then build, then add. Okay. So remove is pretty tiny. Build init is tiny. Build clumps for cluster is big. Build connected components is big. Okay. Yeah, the join step seems to be the biggest step. Although the label is actually pretty big too. Like this might have been a bad spike, an inconsistent spike. So I should probably be averaging all these or taking the outliers, removing the outliers. Find the smallest one for each one. This one's pretty small. No, because it does depend on the cluster. Here the label is pretty big. So maybe it is worth doing that optimization on the label. Was that that was on the clumps for cluster label, I think, not the... Yeah, that's the cluster label. I'm not sure that one's ever high. Connected components label is high, but cluster, yeah, cluster is already small. Build connected components label is occasionally big, and I should check if that's something I can do in fewer steps. Oh, the reason that it's slow is because it's doing a full find on everything. The other one doesn't do a full find, I think. No, it does. They have to do finds. But I guess this is sparse, like this is that bad data structure stuff. And again, prefix with nothings too if you want me to see it, because there's a lot of chat. There's a lot of talking chat that isn't aimed at me, and so I just glance over and look for my name being flagged. So yeah, the two places that are labeled optimize I don't think are showing up. That one is not showing up significantly. The build cluster label. The other one, clump union. Well, that is this step. That is part of the join step. So let's go ahead and do that. I'm not sure it's going to matter, but so we're going to pass one of them in as a bytes packed into a struct. Let's give them the same names. And I can't call it uint8. It's unsigned short. Index. That's unsigned char. Jeez. So that's a CBCC. Of course, if that were true, why can't I do that for the other thing? It's like short. Maybe I should just be doing that for the global thing everywhere, and then this might be more efficient. Why don't I check that? Print screen that so I have some reference. Let's change this to unsigned short clump index unsigned char cluster x. And of course, this could all be different with a different compiler anyway. I should just suppress the timings during the... Sorry. Did I finish my drink? I finished my drink. Shame. All right, here we go now. These look smaller. No, that's, well, yeah, it's up to 5.255. Let's look at the old run. Should have saved one that was just the raw times. 6, 3, 6, 4, 5. Hard to say. Hard to say if that made any difference. Might have. So now this is limited, instead of being 10 bits, it's limited to 8 bits. So we're limited to 32 by 32 times 8 bits. So it's 513. It's limited to 8K by 8K. All right, let's put it back. Let's see how it works if we just unpack this stuff, or repack it differently actually. Okay, so let's do this. Type def struct ECC unpacked clump int cluster x int cluster y signed int clump index. And so we'll pass in an unpacked clump ID for m, and we'll pass in int x, int y, int ID x. So then m, cluster y, cluster x, clump index, and this one is y, x, idx. Why am I doing these differently? You'll see. So then when we call them, this one, we will prepack, unpacked clump ID. Because we reuse that across this loop, and then this one, we will go ahead and pass these. Let's go ahead and stick them in variables just so we don't have that super long line. Gotta check what order these were in. XY index, okay. We don't use that anymore. Trying to type into the screenshot. Okay, it's doing it. Let's break it. 1894, 2146. Look at this. Made a big difference. Nope, here it's a 3677. So who knows? 31. I'm not seeing any 50s though. So it might have actually sped it up by a bit of a significant fraction. Oops, I stopped it before it got to that stage. So this is also that thing you might remember if you watched the whole thing where I mentioned that I was forcing myself to recompute some stuff and that I could be passing around. So I should check which stage that's happening in. Yeah, it looks like I doubled the speed of that join step. No, it didn't double. Well, it's still occasionally bad, but didn't double the speed of the whole thing at all. It was the worst one. And it sped up label as well as join because they both call. Yeah, because they both call. It doesn't call union actually. No, it only calls find. So why would that speed it up? I put global clump ID back, right? Because I didn't want to lose the size. Yeah, I did put it back. So yeah, what was that other thing that I was saying I was forcing myself to recompute? I was passing in the adjacent coordinates. So it was the update add remove. I think these things, I passed this in, and then inside those, which are further down somewhere, in this call, it's forcing it to recompute everything, even though I already had the local coordinates. So the question is add remove ever a significant amount of time? No, not at all. So it's not even worth thinking about. That's the lowest one on the thing. Well, I guess init is lower. All right. So there may be more room for optimization. You want to do a proper profiler to actually check. But for now, we'll just stop there. And turn back on our start timer, end timer inside here. And this one is still going. So now let's look at what the actual times are again. Oh, I actually have to delete it. Dun, 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 dun. All this wasted work. Find where the next one is. There we go. Right, okay, so we're back to this. You see the occasional spikes. But those could be other things happening on the machine. We'd have to correlate two runs and see if they're consistent. I guess I can do that with the second window and break when I see the ones. Oh, that's just a Windows screwing up. Yep, this is consistently high, actually. That's a 2 millisecond one. Wonder why. Let's try it one more time. Make sure it wasn't random. Oops. I'll have to investigate that particular case. I was holding the window. Oh, it went up to 8 milliseconds. That's a different one. I was holding the window, so it may not have been valid. Or the streaming could be, who knows, right? Like, I mean, it's got a ton of cores here, so it ought to be okay. Wow, the init was way faster. Init was only 27. There we go. 2.2. Yeah, so it ain't consistent at all. So it just happened to randomly hit spike on the same one twice. 2210. Yeah. So who knows what that spiking is. Cache behavior, core swapping, something hit. The perfectly timed break is actually not that hard because it's jerkily scrolling. It's only printing erratically, so it's because it saves out a PNG file every so often. So there's a bit of a pause, and that's when I'm breaking. I missed it once though. So now what? I've tested some more cases. I haven't tested every possible thing under the sun, but I'm not sure what else to test. Done some performance testing. Let's give an overview. We need to do this if and f stbcc grid count x log 2. Maybe I should give these simpler names. Oh, and I wanted to performance test changing the cluster size. So that lives in quick. No, it's all nebulous. Cluster, clump, chunk, block, segment. I just randomly use them when they seem appropriate. Like cluster is probably not the best name for a regular grid size. Like that should probably be a tile or a cell or maybe a block even. Maybe even a chunk. So clump was intentionally to capture the notion that it's a freeform shape, that it's not a square. It's some random shape within the square. And yeah, so let's test. Let's try making them bigger and see what happens. They seem higher, I think. And let's try making it smaller. Did I actually pick the exact right size? I mean, it's half. The log 2 is half, which is kind of typically going to be ideal. You break your n by n grid down into square root of n by square root of n chunks that are each square root of n by square root of n tends to be optimal, but it might not actually be. Let's see. This might be a little faster. Hard to say. Need to actually measure the whole thing or something. Hundred 12 milliseconds for the whole thing. I don't care about those figures. Oh, that's definitely faster. And that's slower. So 5.5 is optimal. Let's try mixed. Assuming I didn't get any of my x's and y's backwards, it would crash if I did. That's still slower than the 68. That was the optimal. It's a lot slower. 1.56. That's faster. Is that consistent? No. Nope, I need to be averaging these. It's too fast. Alright. I'll have to restart some of this. Do we have a K? No, we don't. In fact, I'm willing to wait. Let's go to 20. No, let's go ahead and suppress the printing to 0. Printf. Cluster count, no, cluster size X, BCC, cluster size Y. Okay. that way. So let's try that way. Of course, this is all being optimized on this one machine with this one compiler. Not necessarily general at all, but just get an idea. Well, looks like 32 by 32 is going to win here. Who knows why? It's just terrible that I just guessed correctly the first time. I mean, like I said, it is the... Yep, that's the fastest one. It's 32 by 32. So then we'll say if PCC cluster size x log 2 greater than or equal to cluster count x log 2. Let's just drop the log 2s. Or SBCC cluster size y greater than equal SBCC cluster count y, and these all need double underscores. Cluster size x log 2 be smaller than not cluster count, map grid count. So now you can override that externally if you need to for some reason, but I'm not even going to document it yet. What else do I need to do? Anybody remember anything I've said I need to do that I haven't done yet? Let's see how many lines it is now. It's almost 700 lines. Now they've added some documentation, the header file section, a little bits of pieces of other stuff. I wanted to reorder the functions, but I'm not going to do that right now. I'll do that in a later version. Let's check if anything else needs to be static. That's a function, public function, static, static, public function, static, 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 end of file. Let's do this. Kind of nice to have. Likewise for this one. Anything else? Anybody? Ferris? Delete this analysis. Okay. So it may have bugs. I haven't done thorough testing. But let's go ahead and post it, right? Reachability. And we could add diagonal neighbors. Phrase this, do this. Usage, I think. Oh, usage is that, yeah. Have I said anything to me? No. All right, we're just gonna upload it and let the world discover. Because why not? I'm sure it may just like not even compile on other things because I may have forgotten stuff. I'm using size T, so what do I need to include to get size T? Just standard lib. Let's compile it in a different order. See if we catch anything. In case I'm using uint8 still somewhere. which I might be. I'm using assert. And do I have to do anything else? Build, rebuild all. All right. Copy STB connected components to STB. Okay. Which I'm on branch master. YOLO. There we go. Oops. That's a git add it instead of STB adding it. And then tools, metapad, readme.list. How major is this one? Better than this herringbone wing tile. Probably gonna get more use than text edit. Oh, right, these are sorted by categories. I forgot. It's not exactly graphics, is it? Is it game dev? What would you call this? It's graphs rather than the graphics. But that's too close to graphics, so it's confusing. I don't know how many people are going to use it outside of game dev, so maybe I'll call it game dev. Let's just say grids, not say largish, because I don't want to imply that they're out of core or something. Loops that count down to 0, I write like this. And I require my i's to be signed. Which is why I require size t to be signed, except it's not. Yeah, graph is, I don't really want to add a section called graphs. It's in other headers as well, as standard def. Let's just call it MISC. Right, I already have a MISC. We build the readme file. Get status. And we have to add readme and tools readme. Get status. Get commit. To be connected. Oh, well. Add it. And we push it. Rejected. I've touched other libs directly on the net. There we go. It's up. Where's my repressor? Oh, I don't have another one now. All right, that's it for the stream, guys. Thank you for watching. Thank you for helping me fix bugs. I hope you enjoyed chatting with each other that I totally ignored. 654 lines. Hey, wait, that got smaller. It was more than that, wasn't it? Maybe it was only 661. Well, that's it on Twitter. Oh yes, the deletion thing. I didn't even really comment on that, did I? I call it fast delete. It's a well-known technique that you swap the last element in the array down over. Yeah, here it is. You swap the last element in the array down over the element you're deleting, so it changes the order of the list. Right? It's a kind of a gross thing for that reason, but if you didn't have to search it, I do have to search it here. If you didn't have to search it, it can be order 1 if you just know where it is in the list. So that's why you do it. Since I am searching it, I could push everything down and maintain the order, but I don't need the order for any reason. And you know, the compiler can generate this as potentially as a very fast thing because this is actually testing all the fields of the RC. I could do that union trick again, so it's just comparing them binary. Remove clump connection wasn't a performance thing though. And then of course this whole hackery of using the minus inside, this is a lot clearer when it's just, you know, array of I equals array of minus n, right? That's the idiom. Because this has the clump errors, it's a little grosser. So yeah, and it's just, you're swapping down the last one, and then you're decrementing the thing. And so, hey, idiomatically, that just becomes this, you know, which is a little gross. But as I've mentioned in other discussions, one of the nice things about these kind of ugly C idioms, there's this one, and there's the so-called Barrett enumeration, which is the when you're enumerating the vertices. No, wait, it's I equals J plus plus. Is that how it is? Yeah. This will produce. So if you're trying to enumerate the vertices in a thing, you know, this is an idiom that if you don't know it, you have to sit there and decode that that's what it's doing. If you know the idiom, it's great because you just can recognize it. If you don't know the idiom, you have to sit there and figure it out, but you can figure it out, unlike something like operator overloading, where you have no idea what it's doing without going elsewhere in the coding. The nice thing about C idioms is they are always locally interpretable. So. All right, so like I said, that's it. I'll stick around and chat for a little bit, but there haven't been a lot of questions anyway, so probably not for long. But anyway, so yeah, like I said before, thanks for watching, etc. Goodbye.